Every atom in your body is built from prisoners, particles we've never seen alone, not because they're too small, but because the universe forbids it. Try to pull one free, and the act of looking makes more matter instead. So what is a quark? What force keeps it forever confined? And how did that single rule decide what the cosmos could become? Somewhere inside every proton, a law of nature is doing the work of a factory, turning raw energy into the weight of worlds. In that hidden workshop, the universe writes its most stubborn rule in a language we can't directly photograph. To follow that rule, we have to abandon the comforting idea that matter is made of tiny, solid beads. A quark is not a speck you can hold at arm's length. It is an excitation of a field, tagged with a peculiar kind of charge called color. Color is not a metaphor for paint, and it is not a detail we can ignore. It is the bookkeeping system that decides which combinations of quarks may exist as stable, ordinary matter, and which combinations are forbidden to persist. This documentary begins in the most familiar place imaginable. The proton, a particle so ordinary it seems almost dull. Yet inside it, the strong interaction behaves unlike any other force we know, growing more insistent as separation grows. At first, the evidence arrives like a faint pattern in noise, scattering angles, energy loss, sprays of debris that refuse to simplify. We learn to read those patterns as fossils of a deeper event, a moment when something point-like was struck. Then the story turns stranger, because inside a proton is not a miniature solar system. It is a shifting probabilistic choreography of quarks and gluons, where the vacuum itself participates, and the boundaries are drawn by equations. We will see why the strong force cannot be pictured as a simple pull across empty space. It is more like a structure that forms between colored objects, concentrating into a narrow corridor of field energy. Follow that corridor far enough, and you meet the unsettling economy of nature. When the accounting becomes too expensive, reality changes its inventory. Instead of yielding a solitary fragment, the system reorganizes into new, permitted wholes. That single constraint reaches outward into the largest scale we can name. In the first instance after the Big Bang, the universe was not built from atoms or nuclei, but from a searing medium where quarks and gluons were the relevant degrees of freedom. As expansion cooled that primordial fire, the cosmos crossed a threshold, one that quietly determined what kinds of matter could endure and how much mass would be available to make stars, planets, and chemistry. To understand what a quark really is, we also have to understand how physicists come to trust what they cannot isolate. The trail runs through centuries of argument, then through experiments that transformed invisibles into numbers and numbers into reality. And it leads ultimately to machines that do not merely observe nature, but provoke it. Beneath mountains and borders, beams are guided into collision so that, for a fleeting moment, the early universe can be approximated and its aftermath measured. Along the way, we will confront a final inversion of intuition. Most of what you call mass is not a substance stored inside quarks. It is energy under constraint, motion and field trapped by confinement, made heavy by a rule that never relaxes. This is an exploratory journey into quantum chromodynamics, the theory that governs color and its consequences. and into the profound fact that the universe manufactures the matter we touch by forbidding certain outcomes. By the end, particle will feel less like an object and more like a permission slip issued by the vacuum itself. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We'll descend from the history of atoms to the evidence inside the proton, then widen to the early universe and today's colliders. And at every step, one question will sharpen. What kind of thing is a quark when nature only allows it in company? Imagine you could reach inside a proton and grab one quark by itself. You pull, expecting a smaller piece to slide free like a bead. Instead, the harder you pull, the more the universe resists your plan. Quietly at first, then with violent certainty. Energy floods the gap you are creating, and the vacuum answers with new particles. Before any quark escapes, the stretched energy snaps into a quark and an antiquark. You do not get one lonely quark. You get two bound groups, new matter made from the attempt. Picture the scene as if it were visible. A proton is not a little marble with 3 dots inside it. It is a restless, flickering region where quarks and gluons churn, and where empty space is never truly empty. When you try to separate one quark, the field between them does not thin into nothing. It tightens into a narrow tube of energy, like a filament drawn from light itself. Pull harder, and that filament brightens and thickens until it becomes more like a fuse than a thread. This is the unsettling premise of our story. Quarks are among the most fundamental ingredients of ordinary matter, yet no experiment has ever isolated a single quark in the wild. Not in a detector, not in a bottle, not as a free particle crossing space. Every quark we infer is always locked inside something larger, and every attempt to pry one loose ends the same way. The universe lets us see their effects, but not their solitude. That absence is not a small technicality. In particle physics, we are used to catching things one by one. Electrons leave crisp trails in a cloud chamber. Muons punch through layers of metal like heavy cousins of the electron. Even neutrinos, famously elusive, can be counted in vast tanks by the faint flashes they cause. Quarks are different. No track ever begins with a quark entered here, and no detector has ever recorded a quark arriving alone. To feel why that matters, start with the familiar layers of structure. You are made of cells, and cells are made of molecules. Molecules are arrangements of atoms, and atoms are mostly empty space. At the center of each atom sits a nucleus, dense and tiny. Inside that nucleus are protons and neutrons, the particles that set the identity and weight of matter. Inside each proton and neutron are quarks, held together by something stronger than anything else we know. The drop-in scale is almost beyond intuition, so it helps to visualize it. A cell is a city of membranes and chemistry, measured in micrometers. An atom is a vast arena by comparison, where the nucleus is a speck and the electrons occupy a diffuse quantum cloud. The nucleus is smaller again by a factor of about 100,000 in volume, and it carries nearly all the mass. Then, inside the proton, the picture stops being architectural and becomes field-like, more like weather than machinery. Each step down is a change in the rules you can rely on. Cells and molecules behave like objects you can picture and manipulate. Atoms already challenge that picture because electrons are not little planets. They are described by wave functions, by probabilities, and by energy levels that jump rather than slide. Nuclei push further, where quantum rules dominate and distances shrink drastically. Quarks force the deepest shift because they are not standalone objects at all. They are excitations of fields, and their behavior is defined by the field that binds them. Even the word inside becomes slippery here. A quark does not sit at a fixed address, waiting to be pointed at. It is better to imagine a pattern of influence, a set of quantum numbers, and a contribution to a collective state. In a proton, quarks exchange gluons constantly, and the proton's properties emerge from that ceaseless exchange. The proton is stable, but its interior is not still. Here is the rule that makes quarks different from every particle you have met. No isolated quark has ever been observed. This is not a temporary failure of microscopes or engineering. It is a law-like behavior of nature, called confinement. Confinement means quarks cannot be separated into individual detectable particles. They only appear as parts of composite particles, like protons, neutrons, and a zoo of short-lived hadrons. The evidence for confinement is both direct and strangely negative. In high-energy collisions, we see sprays of particles called jets, and those jets behave exactly as if quarks were struck and then tried to fly away. Yet the jets never contain a single quark at the end of the line. Instead, they contain hadrons, bundles that are color neutral, meaning the strong force's charge has been balanced. Nature seems to allow quarks to be hit, jostled, and rearranged, but not to be freed. If confinement is a law, then the next question is unavoidable. What enforces it, and why does the universe care? The answer is the strong nuclear force, the central character of this documentary. It is the force that binds quarks into protons and neutrons. It is also the force that binds protons and neutrons into nuclei through a residual echo of the deeper interaction. Historically, the strong force entered physics as a necessity. Early in the 20th century, scientists learned that the nucleus contains positively charged protons packed into an absurdly small space. Electromagnetism says like charges repel, so nuclei should explode. They do not, which meant another interaction had to exist, short-ranged, powerful, and able to overwhelm electric repulsion at tiny distances. That nuclear binding was later understood as a leftover effect of a deeper force acting between quarks, with gluons as its carriers. We know gravity and electromagnetism by their reach. They fade with distance, and their strength falls away as you separate objects. The strong force behaves differently in the regime where quarks live. Inside a hadron, it does not weaken as you pull quarks apart. It effectively strengthens, as if the quarks are connected by a tightening string. The more you try to separate them, the more energy you store in the field between them. This is one of the most counterintuitive facts in modern science. With electromagnetism, separating charges lowers the field energy in the region between them. With the strong force, the field lines do not spread out into space in the same way. They bundle into a narrow flux tube, concentrating energy rather than diluting it. In plain language, the strong force does not like to be stretched, and it responds by pulling harder. At very short distances, the story changes again. Quarks behave almost as if they are free when they are extremely close, a feature known as asymptotic freedom. That is why high-energy experiments can treat quarks as if they were point-like participants in a collision. But as soon as you try to separate them into independent objects, confinement takes over. Freedom exists only in the tightest quarters, inside the smallest prison. That string-like behavior turns your attempt at liberation into an act of creation. When the stored energy becomes large enough, it is energetically cheaper for the field to produce a new quark and antiquark pair. The string breaks, but it breaks by making new endpoints. Each original quark finds a new partner, and the result is two color-neutral bound states. In this way, confinement hides the quark by multiplying matter, not by letting it go. This is pair production with a distinctly strong force signature. You are not pulling out a piece of the proton like a thread from fabric. You are pumping energy into a field until the field rearranges itself into new particles. The vacuum behaves like an active medium because quantum fields can fluctuate and, when allowed by energy, can crystallize into matter. The dramatic part is not that particles appear, but that the strong force makes that appearance inevitable. This is not a side detail of particle physics. It is one of the reasons matter exists in the form we recognize. Without confinement, quarks could roam freely, and the stable building blocks of chemistry might never form. Protons and neutrons might not be stable objects, and nuclei might not exist. The periodic table would be a different story, or no story at all. The strong force is not just glue. It is a rulebook that decides what can be an object in our universe. Consider what object means at the quantum level. A stable particle is something that can travel, persist, and be counted. Confinement restricts which combinations of quarks can become such countable things. It favors bound states whose strong force charge cancels out, and it punishes any attempt to leave that charge exposed. The result is a universe where matter comes packaged, not loose. The stakes reach back to the beginning. In the first microseconds after the Big Bang, the universe was too hot for confinement to lock quarks away. Quarks and gluons moved in a seething plasma, a state of matter unlike anything in everyday life. Temperatures were so extreme that hadrons could not hold together for long, and the distinction between inside a proton and outside was blurred. As the universe expanded and cooled, a transition occurred. Quarks became confined into hadrons, and the raw ingredients of atoms were born. Later, nuclei formed, then atoms, then stars, then the chemistry that eventually made life. It is worth pausing on that transition because it is a kind of cosmic decision point. When the universe cooled past a critical range, the strong interaction changed its effective behavior, and the Quark-Gluon plasma condensed into hadrons. That moment set the stage for everything that followed, because it determined what stable matter would be made of. How different would the universe look if confinement were weaker, or if it never turned on at all? This arc is not only cosmological, it is experimental. Modern accelerators briefly recreate conditions where quarks behave less confined, producing Quark-Gluon plasma in tiny, short-lived fireballs. Detectors do not catch free quarks even there, but they catch patterns that reveal the plasma's properties. We see jets losing energy as they pass through the plasma, and we infer a medium that flows with remarkably low viscosity. In the lab, we can watch matter approach the boundary between confinement and freedom. That boundary is one of the most important phase changes in the history of the cosmos. Visually, these collisions are like controlled lightning strikes. Two heavy nuclei rush toward each other at near light speed, flattened by relativity into thin pancakes of matter. They overlap for an instant, and the energy density spikes beyond anything found in stars. Then the fireball expands, cools, and hadronizes, turning back into ordinary particles that stream into the detector. We do not see the plasma directly, but we see its fingerprints in the debris. There is another twist hiding in plain sight, and it changes how you think about mass. The mass of your body is not mostly the sum of the masses of fundamental particles. The electrons contribute almost nothing to your weight. Even the quarks inside protons are surprisingly light compared with the proton itself. Most of the mass of ordinary matter comes from energy, stored in the strong interaction fields, and the motion of quarks and gluons inside hadrons. This is one of the most profound applications of Einstein's relation between mass and energy. A proton's mass is not a simple inventory of three quark masses added together. It is the energy of a bound, relativistic system. Quarks moving fast, gluons carrying momentum, and fields storing stress and tension. In everyday language, the proton is heavy because it is busy. Its mass is the price of confinement. This is why a proton weighs what it does. It is not a simple bag of three massive pieces. It is a dynamic bound state, where energy is trapped by confinement and counted as mass. The strong interaction contributes through kinetic energy, through field energy, and through the constant creation and annihilation of quark, antiquark pairs inside the proton's quantum sea. In that sense, the strong force is not only responsible for binding matter, it is responsible for most of the mass of the visible universe. When you stand on a scale, you are measuring energy organized by a field you cannot see. That claim invites a quiet question. If most mass is stored energy, then solid matter is less like a pile of tiny stones and more like a stable knot in a set of fields. The stuff of you is not primarily substance, but structure, patterns that persist because the rules allow them to persist. Confinement is one of those rules, and it is written into the fabric of quantum field theory. So the mystery deepens. We are built from quarks, and quarks cannot be isolated. The force that cages them also creates most of the mass in everything around us. It shaped the early universe, and it still shapes every nucleus today. Yet we have never watched a single quark travel alone from point A to point B. We only see the composite outcomes, the bound states, and the traces they leave. In a sense, we live surrounded by evidence of something we cannot directly display. Every proton in every atom is a sealed chamber, and every chamber contains quarks that never appear as solitary travelers. The strong force is both jailer and architect, preventing escape while building the very objects we call particles. That dual role is what makes it so difficult and so fascinating to understand. That raises the central question of this documentary. What is a quark if it cannot exist as a free particle in our detectors? Why does the strong force confine it? And why does that confinement produce the stable matter we depend on? How did this rule shape the universe's evolution from a hot plasma to atoms and chemistry? And how did we learn to trust a particle we cannot isolate in a science built on observation? The answer begins with how humans learned to see the invisible. Before quarks, there were atoms, once proposed as indivisible and later revealed as structured. The idea of atoms goes back to ancient speculation, but it became scientific only when chemistry and physics forced the issue. Each generation pushed deeper, using new tools and new ideas to infer what could not be directly seen. The same logic that made atoms real will make quarks real, even under confinement. Think of the turning points that made invisibles undeniable. Patterns in chemical reactions hinted at discrete building blocks. Measurements of gases and heat pointed to countless unseen constituents in motion. Later, experiments with electricity and radiation showed that atoms had internal parts, and that matter could be probed by scattering. Again and again, reality announced itself not by being held in a hand, but by leaving consistent, quantitative traces. To understand the smallest prison, we start with the first invisible building block that became undeniable. We start with the atom. Chapter 1 ended with a rule that feels like a refusal. Quarks shape every atom in your body, yet none can travel alone. To understand how science accepts an unseen ingredient, we rewind to the first invisible building block, and we watch an idea harden into evidence. Before quarks, there were atoms, first imagined, then argued, then cautiously modeled, and finally forced into reality by numbers that would not bend. This chapter is the first descent, and it begins where measurement is absent and persuasion does the work. In ancient Greece, Democritus and others proposed Atomos, a word that meant uncuttable, the smallest piece of matter that still mattered. The idea was seductive because it made change and diversity look simple, almost mechanical, as if nature were built from tiny bricks. Different materials could be different arrangements of the same basic pieces. Shift the pattern, and you change the substance. Even the act of breaking a stone, in this view, would be a rearrangement of pieces rather than a transformation of essence. Visually, it is easy to see why the story survived. Imagine a handful of pebbles poured into different molds, and each mold produces a new shape without changing the pebbles themselves. The mind likes that kind of economy, where complexity emerges from rearrangement rather than invention. In a world without microscopes, the metaphor is powerful because it matches what hands and eyes already know about grains, powders, and sand. But Atomos was philosophy, not measurement, and that difference is the first lesson in this descent. No experiment could count atoms, weigh them, or watch them collide, because there were no instruments that could touch such scales. Competing schools argued for continua, elements, and qualities, and the arguments could be brilliant without ever becoming decisive. Aristotle's influence, with matter described by continuous substances and changing qualities, offered a different kind of completeness, one that did not need hidden pellets underneath. For centuries, the atom survived as a useful story, not a demonstrated fact, and that survival tells us something about scientific imagination. An invisible layer can be proposed long before tools can reach it, and the proposal can guide thinking even when it cannot be tested. Yet that gap also hides a danger. When tools finally arrive, the layer often turns out not to be the bottom. The history of matter rewards bold guesses, but it punishes certainty about where the guessing must stop. That pattern will keep repeating, and it is worth noticing how it begins. A fundamental layer is announced, then defended, then refined, and then, almost inevitably, replaced by something deeper. The history of matter is not a straight line downward, but a staircase built from surprises. Each step feels final, until a new technique turns the landing into a trapdoor. The modern descent began when chemistry became quantitative, because numbers are harder to argue with than metaphors. Reactions followed fixed ratios that refused to be negotiated, and those ratios showed up across laboratories and continents. Water formed from hydrogen and oxygen in repeatable proportions, and the proportions stayed the same whether you worked with droplets or oceans. The same stubborn regularity appeared in gases, powders, and crystals, even when the materials were purified and recombined in different ways. Salts and acids combined in small whole number relationships, and those integers felt like fingerprints left by an unseen counting process. If you can only combine in 1-to-1 or 2-to-1 steps, then something underneath may be coming in units. Chemistry began to look like arithmetic performed by nature. The laws of definite and multiple proportions were not poetic laws, but numerical constraints that kept appearing when no one asked them to. John Dalton reframed those ratios as a clue about discrete units, and he did it with a calm, almost accountant-like logic. If matter is made of atoms, then compounds are built from integer counts, because you cannot have half an atom in a stable recipe. The arithmetic of chemistry becomes the shadow of a microscopic census, an indirect tally written into every reaction. Dalton's proposal also carried a quiet discipline. If the numbers are real, then the atoms must be consistent entities, not just convenient symbols. Dalton's atoms were still invisible, but they were no longer optional. The atom became a bookkeeping necessity, even without direct sight, because it explained why ratios were stable and why they were simple. It also gave chemistry a new kind of realism, where formulas were not just symbols, but claims about structure. When chemists wrote H2O, they were no longer merely describing a mixture, but implying a specific microscopic architecture. As chemistry matured, the periodic table sharpened the pressure, and it did so in a way that feels almost cinematic. Mendeleev arranged elements by recurring properties and atomic weights, and the pattern did more than organize what was known. The pattern predicted missing elements before they were found, as if the table were a map with blank spaces labeled in advance. Those predictions were not vague either, because he estimated densities, reactivities, and even the kinds of compounds the missing elements should form. Picture the table as a grid of repeating rhythms, colors, reactivities, densities, cycling like musical themes across rows and columns. When a gap appears, the melody suggests what note should be there, and nature later supplies it. A hidden structure seemed to be organizing matter from below, and the organization looked too disciplined to be a coincidence. The table also hinted that atomic weight was not just a measurement, but a clue that each element carried a characteristic internal count. Still, skeptics could say the atom was only a model, a convenient fiction that made equations behave. Maybe nature only behaved as if it were granular, while remaining continuous underneath, like a fluid that merely imitates discrete steps. Maybe the periodic table was a clever classification of continuous stuff, not proof of little hard units. In that skeptical view, the atom was like an accounting trick, useful, consistent, and possibly untrue. Physics needed a turning point that made atoms hard to deny, and that turning point arrived through motion too small to see directly. In 1827, Robert Brown watched pollen grains jitter in water, and the motion looked random, persistent, and immune to patience. It was not life, and it was not obvious currents, and it did not fade when he waited. The jitter did not care whether the grain was organic pollen or groundstone, which made the effect feel like a property of the fluid itself. The visual is deceptively simple. A bright field under a microscope, a grain like a tiny planet, and a restless wandering that never settles. Brown tried different materials, different dusts, different fragments, and the dance remained. Something in the fluid itself seemed to be doing the pushing. On screen, the path can be traced as a scribble, a nervous line that refuses to smooth out into a drift. For decades, Brownian motion was a puzzle in search of a mechanism, because the motion was too regular in its irregularity. If fluids were continuous, why would a suspended grain dance forever, instead of coming to rest as friction drained its energy? If fluids were particulate, then invisible impacts could buffet the grain from all sides, and the jitter could be a macroscopic trace of microscopic collisions. The key is that the collisions are not coordinated, so the grain never receives a perfectly balanced set of pushes. The key idea is statistical, and it is surprisingly modern. The grain is large enough to see, but small enough to be kicked around by countless smaller things, and those kicks do not cancel perfectly. Over time, the grain's path becomes a record of invisible randomness. In plain terms, the grain is a visible messenger carrying the signature of a hidden crowd. In 1905, Einstein gave Brownian motion a quantitative backbone, and the backbone was made of equations that tied the invisible to the measurable. He linked the grains wandering to temperature, viscosity, and molecular size, using probability as a bridge between scales. Heat, in this view, is not a vague quality. It is the agitation of countless particles. Raise the temperature, and the agitation increases, so the grain's wandering should widen in a predictable way. Einstein turned a curious wiggle into a measurable prediction about atoms, and that shift is crucial for this documentary's logic. A philosophical atom becomes a parameter in an equation, and a parameter can be tested. Jean Perrin later tested the predictions and extracted Avogadro's number, turning a hidden population into a count. The number was enormous, but it was not arbitrary, because different methods converged on the same value. Atoms were no longer a philosophical convenience, because the math demanded a specific density of invisible actors. They were counted indirectly through statistics and motion, and the counting produced a stable value that different experiments converged on. The invisible became real, because it forced a specific, repeatable number onto the visible world. At that point, disbelief began to look less like caution and more like denial of a measurement. That success carried a quiet promise and a looming risk, and science often contains both at once. If atoms could be confirmed by their effects, then deeper layers might also be confirmed the same way, through traces and constraints rather than direct pictures. But once you declare a layer fundamental, you invite the next experiment to break it. The victory of the atom did not end the descent, because it taught physicists how to descend. The break came through electricity and beams in glass tubes, in laboratories lit by sparks and coated with the smell of heated metal. In the late 19th century, cathode rays were mysterious streams that bent in fields, and the bending suggested they carried charge. The question was whether the rays were waves in the ether or particles ripped from matter. The apparatus itself looks like early science fiction: sealed glass, metal electrodes, and a ghostly glow that follows invisible lines. J.J. Thomson measured their deflection and inferred a particle with a fixed charge-to-mass ratio, and the ratio was startlingly large. For a given electric push, these things accelerated far more than any known ion, implying their mass was far smaller than any atom. The electron entered the story as a fragment of matter that behaved consistently across different cathode materials. That consistency mattered because it suggested the electron was universal, not a special product of one metal or one gas. The electron meant the atom was divisible, and the word indivisible suddenly sounded like an old promise that could not be kept. A supposedly indivisible unit had an internal component that could be extracted and guided, and it could be steered by magnets like a tiny compass needle. Fundamental had just been revised by a new instrument and a new measurement. The atom was still real, but it was no longer elementary in the way the name implied. This is one of the documentary's recurring shocks, and it is worth pausing on the feeling of it. The atom had been the smallest unit in many minds, a final bead on the chain of matter. Then a beam in a tube revealed a smaller bead, and the chain continued downward. The emotional shift is subtle but important because it teaches scientists to treat final as a hypothesis rather than a destination. Thomson proposed a model where electrons sat inside a diffuse, positive background, like raisins embedded in a soft pudding. It was an attempt to keep the atom mostly intact while admitting its new part, and it fit the limited evidence available. But models are fragile when a sharper probe arrives, and the next probe would not rely on chemistry or electricity. It would rely on a method that turns impacts into images. It would rely on scattering, which is a way of seeing shape without seeing directly. When you throw something at a target and watch how it bounces, the pattern of deflections becomes a kind of silhouette. Scattering turns impacts into information. In modern terms, it is an early form of tomography, reconstructing an interior from the statistics of what comes out. Ernest Rutherford's group fired alpha particles at thin gold foil, using radioactive sources as natural particle guns. Most passed through with little deflection, as if the atom were empty, and that emptiness was already a clue. A small fraction bounced back at large angles, as if they hit something dense, and the rarity of those events made them even more dramatic. It was like firing bullets at fog, and occasionally hearing a sharp ping, as if a hidden metal bead were suspended inside. The visual here is stark. A narrow beam, a sheet of gold so thin it is almost not there, and a ring of tiny flashes on a screen that records where particles land. Most flashes cluster forward, but a few appear where they should not, like ricochets from an invisible wall. The pattern was too extreme for a smeared-out positive charge. On a graph, the tail of large-angle scattering stands out like an accusation. Rutherford concluded the atom has a tiny nucleus, and the conclusion rearranged the mental picture of matter. Nearly all the positive charge and mass are concentrated in a compact center, and the electrons must occupy the vast surrounding space. The atom became mostly emptiness, with structure hidden in a minute core. The nucleus was not just a new part, but a new scale, and scale is where physics changes its rules. This was another shock of scale and intuition, because solidity is not what it seems. The solid world is built from atoms that are mostly void, and the void is not a poetic exaggeration. The mass is not spread out where the volume is, and ordinary pictures fail because our senses evolved for surfaces, not for probability clouds. What feels like hardness is really electromagnetic repulsion between electron structures, a force field handshake that never allows true contact. If you could scale an atom up to the size of a stadium, the nucleus would be a speck near the center, and the electrons would define the space by their allowed patterns. That analogy is imperfect, but it conveys the imbalance. Matter is not packed like a rock. It is structured like a sparse architecture held together by forces. In visuals, the emptiness should feel almost unsettling, because the everyday world is built from what is mostly not there. The nucleus also changed the documentary's trajectory because it pointed toward the region where mass and identity concentrate. Chapter 1 began inside the proton, where confinement rules, and Rutherford pointed to the gateway that leads there. If you want to understand matter's weight and identity, you must understand the nucleus. And if you want to understand the nucleus, you must understand what the nucleus is made of. To talk about nuclei, we need a new unit of distance, because our usual scales collapse. Atomic sizes are measured in angstroms, around 10 meters, and even that is already beyond ordinary imagination. Nuclear sizes are measured in femtometers, around 10-15 meters, and the shift is not just a smaller number. It is a migration into a domain where the vocabulary of everyday space becomes unreliable. That is a factor of 100,000 in length, and far more in volume, because volume shrinks with the cube. The nucleus is not a slightly smaller atom. It is a different regime. When you compress a region by that much, forces and quantum rules change their relative importance. The same equations can still apply, but the balance of terms becomes unfamiliar, and unfamiliar balances create new phenomena. At femtometer scales, forces reorder their hierarchy, and the familiar pecking order becomes meaningless. Gravity is irrelevant, not because it disappears, but because it is too weak to matter among such small masses. Electromagnetism becomes brutally strong, and quantum behavior is not a correction, it is the language. The nucleus is a place where energy scales are so high that even rest is a dynamic, fluctuating condition. Classical intuition about orbits and trajectories becomes a misleading metaphor, because particles do not behave like tiny planets. They behave like quantum objects with constrained possibilities, and those constraints show up as discrete energies and probabilities. In plain terms, the nucleus is not a miniature solar system. It is a compact quantum arena. If we draw orbits, we are really drawing expectations, not paths, and that distinction matters more as the arena shrinks. Early nuclear models treated the nucleus as a cluster of protons and electrons, because those were the known pieces, and the urge to reuse known parts is natural. That picture struggled immediately, because electrons confined to such a small region would carry enormous momentum. The uncertainty principle makes that unavoidable. Squeeze position tightly, and momentum spreads wildly. The implied energies were so large that the nucleus should behave nothing like what experiments showed. The numbers did not fit, and the nucleus seemed to be hiding a missing ingredient. Beta decay, where electrons emerge from nuclei, made the confusion worse because it looked like electrons were inside and then escaped. The data hinted that something subtler was happening, but the vocabulary was not ready. The nucleus was acting like a machine with a missing gear, producing outputs that did not match the parts we thought were inside. In 1932, James Chadwick found that missing ingredient, and the discovery was both simple and profound. He identified the neutron as a neutral particle with nearly the proton's mass. inferred from how radiation knocked protons out of materials. Neutrality mattered because it allowed mass without charge, and it allowed nuclei to vary without changing chemistry. A neutral particle can slip into the nucleus without altering the electron structure that defines an element's chemical personality. The nucleus could now be built from protons and neutrons without stuffing electrons into an impossible space. Isotopes made sense as different neutron counts, and the periodic table gained a deeper explanation for why elements could have multiple masses. The nucleus became a countable composition, not a mysterious blob. In visuals, the nucleus can now be shown as a tight cluster of two similar beads, one charged, one uncharged, locked in close contact. With protons and neutrons, the nuclear picture became clearer and more troubling because clarity exposed a paradox. Protons are positively charged, and like charges repel with a force that grows as distance shrinks. Pack several protons into a femtometer scale region, and electromagnetism predicts violent explosion. The closer they are forced together, the more intense the repulsion becomes, and the nucleus should fly apart like a compressed spring. Yet many nuclei are stable for billions of years, and their stability is not delicate. They sit at the center of atoms through geological time, surviving heat, pressure, and cosmic radiation, and they do so with protons pressed uncomfortably close. Something must be countering the repulsion, and it must be doing it relentlessly. The stability is not an exception, but a widespread fact, which means the counterforce must be a basic feature of nature. So a new force had to exist, or an old force had to behave in a new way, and either option was radical. The stabilizing interaction had to be stronger than electromagnetism at short range, because it wins inside the nucleus. It had to fade quickly beyond the nucleus, or chemistry would be unrecognizable, and atoms would stick together in strange ways. That short reach is not a minor detail, because it explains why the world is not one giant nuclear clump. It had to bind nucleons without caring about electric charge, because neutrons and protons both participate in the glue. It also had to be selective in distance, strong when nucleons nearly touch, and weak when they separate by a few femtometers. That combination of strength and short reach is unusual in everyday experience. In human-scale life, strong forces usually act across visible distances, but here strength comes with a strict cutoff. Physicists called it the nuclear force, and the name is almost modest compared to its consequences. In modern language, it is the residual strong force, an echo of a deeper interaction that acts inside protons and neutrons. It is powerful, short-range, and saturating, meaning each nucleon mostly binds to near neighbors rather than to every nucleon at once. That saturation is why nuclear matter has a roughly constant density, even as nuclei grow larger. Saturation explains why nuclei have a limited size and a characteristic density instead of collapsing into ever tighter balls. It also explains why adding nucleons does not increase binding indefinitely, and why heavy nuclei can become unstable. The nucleus is not held together by a simple all-to-all attraction. It is held together by a force with rules. Those rules create a landscape of stable and unstable isotopes, a chart of what nature allows to persist. This residual force is already a clue about the quark world, even if we do not name quarks yet. Residual forces often hint at a more fundamental one underneath, like the way molecular forces arise from electromagnetism between neutral atoms. Nuclear forces look like the leftover of something acting inside protons and neutrons, leaking out just enough to bind them. The nucleus, in that sense, is a shadow cast by deeper charges that we have not yet identified. The range of the nuclear force is only a few femtometers, and beyond that it drops rapidly, leaving electromagnetism to dominate again. That is why nuclei are tiny islands inside much larger atoms, and why the atom's chemistry is governed by electrons rather than by nuclear glue. It is also why the nucleus is a special arena, where the rules change abruptly with distance. Step outward by a few femtometers, and the dominant interaction flips, like crossing a border. If you could watch forces as colors on a scale, electromagnetism would flood the atomic volume, while the nuclear force would flare only at the center. The transition would look like a boundary layer, a sudden shift in which interaction matters. Nature, at small scales, is organized by thresholds. Those thresholds are not just scientific details, because they decide what kinds of structures can exist in the universe. The nucleus, therefore, becomes a boundary in our descent, and boundaries are where new physics tends to appear. Above it, chemistry and electromagnetism organize matter, setting the shapes of molecules and the textures of materials. Inside it, a different interaction sets stability and mass, deciding which isotopes exist and which decay away. The nucleus is where identity becomes physical, because it is where the element's charge is anchored. And inside the particles that make the nucleus, an even deeper rule will appear, one that Chapter 1 introduced as confinement. The nucleus is not merely a container, it is a sign that the story continues inward. Each boundary invites the next question. If the nuclear force is an echo, what is it echoing, and why does the echo stop so quickly outside the nucleus? At first, protons and neutrons were treated as elementary because they behaved like sturdy building blocks in early experiments. They were the heavy pieces, and the nucleus seemed like the final layer, a compact core beyond which there was nothing to see. But the logic of the last century warns us against that comfort. Even sturdy can be a sign of hidden structure, because composites can look simple until you hit them hard enough. Each time we declare a bottom, experiments find structure, and the discovery is usually driven by a new way of probing. Sometimes it is a beam in a tube, sometimes it is scattering off foil, and sometimes it is a statistical argument that turns noise into signal. The descent is powered by technique as much as by theory. Better sources, better detectors, and better mathematics repeatedly turn the invisible into something that can be constrained. The nuclear force sharpened the suspicion because it looked like a leftover rather than a primary rule. If it is residual, then there must be a primary strong interaction beneath it, acting on constituents inside nucleons. If protons and neutrons feel a leftover attraction, then something inside them is exchanging something more fundamental. The nucleus becomes a kind of forensic scene because it shows effects that the visible participants cannot fully explain. The nucleus is not the end of the story, it is the signpost, and signposts point beyond themselves. The very existence of a short-range glue implies an internal mechanism, because nature rarely offers a force without a carrier and a charge. Even before the details were known, the shape of the problem was clear. If the glue has a range, then something sets that range, and range is a clue to underlying dynamics. This is where Chapter 1's confinement returns as a historical problem, not just a modern statement. The strong interaction that cages quarks also leaves a trace between nucleons, and we meet it first as nuclear binding rather than as quark confinement. The same rule will explain both, but only after we accept that protons are composite. The descent is about accepting that the familiar pieces may themselves be built from stranger ones. The descent into the invisible has a repeating rhythm, and this chapter has traced its first full cycle. Philosophy proposes a smallest unit because the mind wants a clean foundation. Chemistry hints at discreteness through ratios, and the periodic table turns those hints into a structured demand. The demand is not aesthetic because it produces predictions that can be wrong, and wrong predictions are where science becomes sharp. Statistical physics forces atoms into reality through Brownian motion, converting jitter into evidence. Electricity reveals the electron and breaks indivisibility, showing that uncuttable was a temporary label. Scattering reveals the nucleus and makes emptiness central, replacing solid pictures with sparse architecture. Each step changes not only what we think matter is, but what we think it means to know something unseen. Then nuclear physics adds the neutron and exposes a paradox that cannot be ignored. Protons should repel, yet nuclei hold together, and the stability is too strong to be an accident. A short-range force appears, strong enough to overwhelm electromagnetism in a tiny domain, and its existence is an invitation to dig deeper. What looks like a simple glue becomes a sign that the true binding mechanism is hidden inside the nucleons themselves. If confinement is a law, then the next question is unavoidable. What is the deeper interaction that binds quarks, and why does it only allow color-neutral matter? To answer that, we have to step through the nucleus and into the proton, following the trail from residual glue to fundamental charge. The next chapter follows the evidence that protons are not elementary and that the strong force has a hidden charge. The descent continues, but now the rules become stranger. When the probe becomes energetic enough, the proton stops looking like a smooth bead and starts looking like a seething interior. That raises the central question of this documentary. What is a quark? Why can't it ever be observed alone? And how did that single rule shape the matter of the cosmos? We began with Atomos, the uncuttable, a philosophical boundary drawn with confidence and no instruments. We end with a nucleus that is cuttable in principle, but guarded by a force that behaves unlike any other. Short range, saturating, and suggestive of deeper structure. The gateway is open, and the quark world waits on the other side. Protons and neutrons once looked like final building blocks, sturdy and indivisible in early detectors, where tracks ended cleanly and charges came in familiar whole numbers. Chapter 2 showed how scattering exposed hidden structure in atoms and nuclei, turning vague solids into layered systems with cores and shells. Now the same logic turns inward, toward the nucleon itself, and toward the question of whether nuclear matter has its own deeper architecture. By the middle of the 20th century, physics enters the particle zoo era, driven by cosmic rays and by accelerators that can finally create new matter on demand. In cloud chambers and bubble chambers, photographs fill with curling trails, sudden kinks, and forked decays that look like tiny lightning bolts frozen in time. Detectors begin to register showers of short-lived hadrons, each with its own mass and decay pattern, and each appearing as a brief signature rather than a stable object. Pions, kaons, lambdas, sigmas, and deltas multiply faster than intuition can organize, and the naming itself starts to feel like triage. At first, the zoo feels like chaos, a catalog without a grammar, because each new resonance seems to add a new exception. Many of these particles live for tiny fractions of a second, yet they appear in repeatable families across different experiments and different machines. Their lifetimes and decay routes show rules, even when the list feels endless, and the rules are written in branching ratios and angular distributions. Even the way tracks curve in magnetic fields becomes part of the story, because curvature reveals momentum, while ionization hints at mass. The strong interaction is the common thread, because these new particles are hadrons, meaning they participate in the force that binds nuclei. They are produced copiously in high-energy collisions, and they decay through characteristic pathways that often begin with the strong force and end with the weak. The question becomes structural rather than merely taxonomic, because the patterns look too clean to be random. What are hadrons made of, and why do their properties cluster into repeating motifs? Physicists notice regularities that look like symmetry, not coincidence, and symmetry is a powerful word in modern physics. Certain particles come in multiplets with related masses and charges, as if they were different orientations of one underlying object. The patterns resemble the periodic table's early hints, where classification preceded mechanism, and where order arrived before anyone knew about electrons. In the zoo, the chemical families are not elements but hadrons, and the valence is not chemistry, but quantum number bookkeeping. This is where Murray Gell-Mann and George Zweig propose a radical bookkeeping tool, at a time when the community still debates what counts as real. They suggest that hadrons are composites of more basic entities, arranged in simple combinations that generate the observed families. The goal is not to see these entities directly, because nothing in the detectors looks like a free subparticle. The goal is to explain the repeating structure of the zoo with a minimal alphabet, the way a few letters can generate many words. They call the constituents quarks, and they start with 3 flavors, a term borrowed from everyday language, but used here with strict mathematical meaning. Up, down, and strange are labels for distinct quantum states, not flavors in any ordinary sense, and they behave like coordinates in an abstract symmetry space. With just these 3, many hadrons fall into orderly groups, and the zoo begins to look like a coded message rather than a list. The Quark model is daring because it compresses complexity into a small set of rules, and compression is often where truth hides. The proton and neutron become the simplest test case because they anchor ordinary matter and because their properties are measured with extraordinary precision. In the Quark model, a proton is 2 up quarks and 1 down quark, written as U-Ud in the new shorthand. A neutron is 1 up quark and 2 down quarks, written as Ud, and the swap explains why they are so similar in mass, yet different in charge. Even before anyone talks about gluons or fields, this simple counting already feels like a map. This immediately forces a shocking claim about electric charge, because the arithmetic of the proton and neutron refuses to work with whole number constituents. Quarks must carry fractional charges, unlike any isolated particle ever measured in nature. Up carries plus 2/3, and down carries minus 1/3. And these fractions are not approximations but exact assignments within the model. The claim is radical not because the math is hard, but because the implication collides with decades of experimental habit. The arithmetic is simple, and the implication is not, because it asks us to accept that the universe can contain hidden fractions, while only showing us integers. 2 ups and 1 down add to +1, matching the proton's observed charge, and the match is so clean it feels engineered. 1 up and 2 downs add to 0, matching the neutron's neutrality, and suddenly neutrality looks like a balance rather than an absence. A familiar world of whole charges is rebuilt from unseen pieces that never appear alone. Fractional charge is radical because charge had always appeared in integer units in isolation, and isolation is how classical intuition defines a particle. Electrons carry -1, protons carry +1, and ions come in whole steps, as if nature were counting on a discrete dial. The quark model asks us to accept hidden fractions that never appear alone, and it asks that without offering a photograph of a single quark track. It is a theory that begins as an explanation of patterns, not as a direct discovery. The zoo's patterns strengthen the case, because the same charge assignments explain many hadrons at once, and breadth is persuasive in physics. Mesons fit as quark and antiquark pairs, with charges that add to integers, which is why mesons can be observed as whole charge particles. Baryons fit as 3 quark combinations, again producing whole charges in every observable particle, and the bookkeeping stays consistent across dozens of states. The model does not merely fit one object. It fits an entire menagerie with one set of rules. Strangeness becomes a key clue because it behaves like a conserved label in strong processes, and conservation laws are the fingerprints of hidden structure. Strange particles are produced readily by the strong force, often in pairs, but they decay more slowly through the weak force, leaving tracks that travel centimeters before splitting. That delay is visually dramatic in bubble chamber film, where a neutral particle leaves no track until it decays into charged daughters. The quark model turns strangeness into the presence of a strange quark, making conservation rules look like constituent accounting rather than magic. Classification becomes prediction, not just organization, and prediction is where a model risks embarrassment. The symmetry scheme implies missing members of multiplets that should exist, with specific charges and masses that can be calculated within the framework. When the omega minus is discovered with the predicted properties, including its charge and its unusually narrow decay behavior, the zoo looks less like a mess and more like a deciphered code. The moment is historically important because it turns a tidy chart into a claim about what nature must contain. Still, a classification tool is not the same as evidence of physical constituents, and many physicists are cautious for good reasons. Skeptics can say quarks are mathematical fictions, like epicycles that organize data without being real, and history has examples of useful fictions. A symmetry can be an emergent pattern rather than a microscopic truth, and the line between the two is not always obvious. To move from pattern to substance, physics needs a probe that can strike inside the proton, not merely sort hadrons into families. That probe is scattering, the same method that revealed the nucleus, and it works because waves reveal structure through interference and deflection. If you want to test whether a target has internal parts, you hit it with something energetic and watch the angles and energies that come back. The higher the energy, the shorter the effective wavelength, and the finer the detail you can resolve, like switching from a blurry lamp to a sharp laser. In quantum mechanics, resolution is not a metaphor. It is a relationship between momentum transfer and spatial scale. In the late 1960s at SLAC, electrons become the projectile of choice, and the setting itself feels like a new era of precision. They are point-like as far as experiments can tell, and they interact electromagnetically in a clean, calculable way, without the messy, strong-force complications of hadron beams. Fire them at protons with enough energy, and the proton stops acting like a smooth object, the way a solid wall stops looking smooth under a microscope. The accelerator's long, straight sections and carefully tuned beams turn the proton into a target for controlled interrogation. The experiments measure deep, inelastic scattering, where the proton is not merely deflected, but broken into a spray of hadrons that fills the detectors downstream. Deep refers to large momentum transfer, and inelastic means energy goes into internal disruption rather than simple recoil. The key result is in the electron's energy loss and scattering angle, which encode the target's internal momentum distribution through variables that can be compared across energies. The data refuse to match a picture of a featureless proton, even when theorists try to smooth the curves with every reasonable correction. Instead, the electron behaves as if it is scattering off point-like constituents inside the proton, and the statistics sharpen that impression rather than blur it. The cross-sections show scaling behavior, meaning certain combinations of measured quantities depend weakly on the overall beam energy. Scaling suggests the electron sees hard, localized charges, not a soft smear of charge spread evenly through space. The proton looks, in this limited sense, like a bundle of smaller things, and the bundle has a measurable internal momentum structure. Richard Feynman introduces the language of partons to describe what the electron hits, choosing a term that keeps the interpretation flexible. Partons are the effective constituents seen in a fast-moving proton, carrying fractions of its momentum, and their distribution can be extracted from the scattering data. The word is deliberately cautious because the experiments reveal behavior before they reveal identity, and because the proton is a relativistic object whose internal picture depends on the frame. In the parton model, the collision is so fast that the constituents look frozen during the impact. The connection to quarks becomes compelling because the partons carry electric charge, and charge controls how strongly electrons scatter. The scattering strength depends on the square of charge, and the pattern fits fractional charges rather than integer ones, which is a subtle but decisive clue. If the proton's constituents had integer charges, the scaling curves would land in different places, and the mismatch would persist across datasets. The simplest match is that the charged partons are quarks, and the quark model gains a new kind of evidence that reaches inside. But the match is not perfect if you only count 3 quarks, and the imperfection is as informative as the success. The momentum carried by the charged partons does not add up to the proton's full momentum, even after experimental uncertainties are accounted for. Something else inside the proton must carry momentum while remaining electrically neutral, and the missing momentum is not a small correction. The proton, it turns out, is not mostly made of the charges we can see. It is mostly made of something that does not couple directly to the electron's charge. This is where gluons enter as a necessity, not a decoration, because binding in quantum field theory is never free. If quarks are the charged constituents, then a strong binding agent must also exist, and and it must carry energy and momentum of its own. That agent must be able to interact with itself in a way photons do not, because the strong force behaves differently from electromagnetism at large distances. The data are telling us that the proton's interior is dominated by field energy, not by a simple inventory of 3 particles. The Quark model also runs into a deeper quantum problem, and it appears in a place where classification meets fundamental principle. Some baryons appear to contain 3 identical quarks in the same spatial and spin state, which seems forbidden by the Pauli exclusion principle. If quarks are fermions, something must distinguish otherwise identical quarks, or the model collapses under the weight of quantum statistics. This is not a minor technicality, because the exclusion principle is one of the most tested rules in physics. The solution is a new kind of charge called color, and the name is playful, but the concept is exact. Color is not visual color, and it is not optional bookkeeping once the theory matures, because it changes what counts as identical. It is a quantum label with 3 values, allowing quarks to differ while sharing flavor and spin, so 3 quarks can occupy a symmetric spatial state without violating fermionic anti-symmetry. The proton becomes not just UUD, but UU'd with 3 distinct color labels that cancel in the observable whole. At first, color can sound like a trick to fix counting, and in its earliest form it is introduced with that modesty. Yet it quickly becomes more than a label, because it organizes how the strong force must work if it is to be consistent and predictive. If color is a charge, then there must be a field that couples to it, and carriers that transmit it, just as electric charge implies an electromagnetic field. The bookkeeping turns into dynamics, and dynamics is where a theory becomes physical. Those carriers are gluons, and they themselves carry color charge, which is the detail that makes the strong force feel alien. That single fact changes everything about the force, because it means the field can act on itself and can reshape its own lines of influence. Photons do not carry electric charge, so electromagnetism does not bind itself into tubes, and its field lines spread outward. Gluons do carry color, so the strong field can interact with itself and concentrate, producing behavior that has no simple classical analog. Quantum chromodynamics, or QCD, is the theory that results when color becomes a gauge symmetry, and gauge is the technical word for a symmetry that demands a force field. The strong force is no longer a vague nuclear glue, but a precise field theory with quarks and gluons as its degrees of freedom, constrained by mathematical consistency. In QCD, the proton is not 3 beads held by a string, even if that picture is tempting for the imagination. It is a bound state in a non-linear field, where energy, momentum, and quantum numbers are shared across a restless interior. This is the modern definition shift that matters for the central question, because it protects us from the wrong mental images. A quark is not a tiny billiard ball hiding inside the proton, waiting to be plucked out with better tweezers. A quark is an excitation of a quantum field, defined by its quantum numbers and its interactions, and its existence is tied to the rules of the field. In that sense, asking for a quark's size is like asking for the size of a ripple in the ocean, unless you specify how you are measuring it. Experiments have searched for a quark size, and they keep finding none, pushing the limit to smaller and smaller distances. In scattering, quarks behave as point-like down to the smallest distances we can probe, meaning the data show no deviation from a point-like interaction. That does not mean they are classical points, because classical points would create infinities without quantum renormalization. It means no internal structure has been detected within present resolution, and the field description remains intact. Quarks carry spin 1/2, and they carry electric charge in fractional units, which determines how they respond to electromagnetic probes. They also carry color charge, which is the source of the strong interaction, and color is why quarks cannot be treated as isolated objects in the usual way. Flavor labels like up, down, and strange track how quarks transform under the weak interaction and how they contribute to hadron properties, including masses and decay patterns. The labels are not decorations. They are the coordinates of how quarks participate in nature's forces. The proton, in this view, is a dynamic system, not a static trio, and the word dynamic is literal. It contains valence quarks that set its net quantum numbers, including its overall charge and baryon number, which remain fixed. It also contains a sea of quark-antiquark pairs and a dense population of gluons, constantly created and reabsorbed as allowed by quantum fluctuations. The interior is less like a solar system and more like a storm, with transient structures that appear and vanish while the whole remains stable. Deep inelastic scattering makes that dynamism measurable because the probe's energy determines what parts of the storm become visible. As the probing energy increases, the effective number of partons grows, reflecting more resolved gluon activity and more resolved quark-antiquark pairs. The proton's interior looks more crowded at higher resolution because field fluctuations become visible as constituents, and the distribution of momentum shifts toward gluons. The proton is not a fixed picture. It is a scale-dependent portrait. This is where a common misconception must be cut off early, because it can poison everything that follows. Quarks are not little marbles orbiting inside a proton like planets around a sun, and there is no classical trajectory you could draw even in principle. The proton is a quantum-bound state, where what counts as a constituent depends on the energy scale of the probe, and where inside is a statistical statement. When we say 3 quarks, we mean 3 valence quantum numbers, not 3 permanent pellets. Yet the experiments also insist on something else that feels contradictory, and the contradiction is the source of the chapter's mystery. When struck hard, quarks act like quasi-free point particles in the instant of scattering, as if the proton momentarily stops being a bound object. The data show asymptotic freedom, where interactions weaken at very short distances, and this weakening is encoded in how the effective coupling changes with momentum transfer. The strong force, paradoxically, becomes weaker when quarks are close together, which is the opposite of many everyday forces. So the tension sharpens into a single question that drives the rest of the film, and it is a question with experimental teeth. If quarks can behave like free particles when hit hard enough, why can we never pull one out and watch it travel alone? Why does the universe allow point-like scattering evidence, but forbid isolated detection, even in the cleanest detectors built by human hands? What kind of rule lets us glimpse the pieces, yet prevents us from owning them? The answer cannot be that quarks are merely hidden by smallness, because the same experiments that reveal point-like behavior also show what happens afterward. The final states are always hadrons, and the debris organizes into jets, collimated sprays that carry the memory of an underlying quark or gluon direction. Every quark-like event ends as jets of color-neutral particles, never as a lone fractional charge, and the absence is as striking as any presence. The detectors see plenty of charged tracks, but never the unmistakable signature of a free 2/3 charge drifting away. Color explains why the strong force is unlike electromagnetism at large separation, and the difference begins with the geometry of field lines. Electric field lines spread outward, so the force weakens with distance, and the energy is distributed through a growing volume of space. Color field lines tend to bundle because gluons interact with each other and keep the field confined, and confinement changes the way energy scales with separation. Instead of diluting, the field resists being stretched, as if space itself were reluctant to host isolated color. That bundling is the first hint of confinement in modern terms, and it can be described without pretending we can see the field directly. Separate colored objects, and the energy in the field does not dilute because the field does not spread freely in all directions. It grows, storing energy in a narrow tube that resists extension, and the tube behaves like a taut connection rather than a fading influence. The more you pull, the more energy you pour into the link, and the link does not politely weaken. In practice, trying to isolate a quark becomes an act of energy injection, and the energy has somewhere to go. Past a threshold, the field produces new quark-antiquark pairs, and the would-be isolated quark is immediately rebound into a color-neutral hadron. The attempt creates more hadrons rather than freeing one quark, and the detector records a richer spray instead of a liberated fraction. The universe answers the extraction attempt by manufacturing new composites, as if it refuses to allow color to remain exposed. This is why fractional charges can exist without ever appearing alone, and why the quark model can be both correct and frustrating. The fractions are real properties of quark fields, but confinement prevents them from being observed as isolated particles, even when the collision energy is enormous. Nature hides the fraction by enforcing that observable states have integer total charge, and it does so through the dynamics of the strong field rather than through a simple prohibition. The rule is not quarks are too small, but colored objects cannot be separated into asymptotic free states. The logic loops back to the documentary's opening hook, and it lands with a strange kind of intimacy. Every atom in your body is built from quarks, yet no quark crosses a detector by itself, not in cosmic rays and not in colliders. The evidence is overwhelming, but it is indirect by design, because the strong force controls what can be seen and what can only be inferred. We learn about quarks the way we learn about wind, by watching what it moves, not by catching it in a jar. We now have two pillars of evidence that converge on the same conclusion, and their convergence is what gives the story its solidity. The particle zoo reveals symmetry patterns that demand quark constituents with specific charges and flavors, and it does so across a wide range of hadrons. Deep, inelastic scattering reveals point-like charged partons inside the proton, matching those quark charges and implying gluons carry much of the momentum. One pillar is classification with predictive power, and the other is a direct internal probe that measures how momentum and charge are distributed. And we have a modern definition that prevents old misunderstandings, because language can trap the imagination in the wrong era. Quarks are field excitations with quantum numbers, not miniature objects with fixed trajectories. and their reality is expressed through consistent interactions and measurable consequences. The proton is a bound state of quarks and gluons, with properties emerging from collective dynamics, including spin contributions and momentum sharing. When we say inside, we mean a structure revealed by scattering, not a little box with 3 permanent occupants. But the central mystery remains intact, and it is now sharper because the evidence is sharper. The proton looks divisible under extreme probing, yet it never yields a free piece, and every attempt to isolate a fraction ends in new composites. The same theory that makes quarks real also makes their solitude impossible, and that is not a philosophical flourish, but a physical constraint. We can hit the proton hard enough to see point-like behavior, yet not hard enough to violate confinement, because confinement is not a matter of insufficient force. If confinement is a law, then the next question is unavoidable. What kind of force grows stronger as you try to separate its charges, and how does that rule manufacture the mass of matter? Why does most of the proton's mass arise not from the bare masses of quarks, but from the energy stored in motion and fields, according to Einstein's relation between energy and mass? When you hold a proton in your hand, what you are holding is largely the energy of QCD trapped in a stable pattern. We enter QCD next, where the strong force does not weaken with distance the way we expect. The theory will explain why quarks look free at short range, yet become more tightly imprisoned as the gap widens, and it will show how a simple symmetry becomes a universe of emergent phenomena. The deeper we look into the proton, the more we find that empty space is not empty at all. Yet the rules remain exact, and the mystery remains disciplined. We have a name for the rule that cages quarks, but a name is not a mechanism. QCD is the mechanism, and it is not a metaphorical glue. It is a quantum field theory with strict symmetries, precise equations, and consequences that feel almost theatrical when translated into pictures. Quantum chromodynamics describes the strong interaction, the force that governs quarks and gluons inside hadrons. It is a gauge theory, built on an internal symmetry, and that symmetry is not about space. It is about an abstract color degree of freedom, real in its effects, even if the words are borrowed. In a gauge theory, the symmetry is local, meaning it can vary from point to point. That local freedom is not optional. It forces the existence of a compensating field, and in QCD, that field is the gluon. In QCD, quarks carry a charge that is not electric charge. They carry color charge, with 3 types we label red, green, and blue. The labels are metaphors, yet the bookkeeping is physical, because color determines which gluon interactions are allowed. Color is also conserved in every interaction, the way electric charge is conserved. That conservation is not a moral rule. It is built into the symmetry that defines the theory. If the word color feels playful, the math is not. Color is tied to the SU3 gauge symmetry, which means the theory has 8 gluon fields rather than 1. That number is not chosen for convenience. It falls out of the symmetry's structure, like notes fixed by an instrument. SU3 has 8 independent generators, and each generator corresponds to a distinct gluon field component. When we say 8 gluons, we are really naming 8 ways the color field can twist. The strong force is mediated by gluons, the gauge bosons of color. Like photons, gluons are force carriers, and they appear as quanta of a field. Yet the similarity ends quickly because the strong field is built to interact with itself. That self-interaction is not a small correction. It is the defining feature of the strong force at hadron scales. Even the vacuum in QCD behaves like an active participant rather than an empty stage. Photons carry no electric charge, so light does not pull on light in ordinary vacuum. In classical electromagnetism, field lines spread outward, and the superposition principle keeps the equations linear. You can add two electromagnetic waves, and they mostly pass through each other unchanged. The linearity is why the electromagnetic field often feels geometrically simple, like ripples spreading on an open pond. Gluons carry color charge themselves, and that single fact changes the geometry of the field. The strong field can interact with itself because the carriers are also charged under the same force. The equations become nonlinear, and the field stops behaving like the familiar, politely spreading lines of electromagnetism. Nonlinearity means the field can concentrate, knot, and reinforce itself, an interaction that has no direct classical analog in everyday experience. Visually, imagine two quarks as bright points in a dark void. In an electric field, you would draw lines that fan outward, thinning as they fill a growing sphere. In QCD, the picture tightens. Lines crowd together as though space has learned to braid. The darkness between the quarks does not look empty anymore. It looks threaded, as if a hidden fiber is being spun between them. Electromagnetic force weakens with distance because its field dilutes through space. The energy of the electric field spreads outward, and the force falls roughly with the square of separation. QCD does not grant color that freedom at hadron scales, where quarks live. The color field does not simply disperse because gluon self-interactions alter how the field energy arranges itself. Instead of relaxing outward, it prefers to stay confined, concentrated, and costly. Between colored objects, the color field tends to bundle into a narrow connection. Instead of filling a growing volume, it concentrates into a tube of field energy. This is the flux tube picture, and it is the first way to make confinement feel tangible. The tube is not a literal rope, yet it behaves like one in the energy accounting. It is a visualization of how the field stores energy when it cannot spread freely. A flux tube behaves less like a fading influence and more like a stretched string. Pull the quarks apart, and the tube lengthens without thinning much. The stored energy rises roughly linearly with distance, like a rubber band that refuses to relax. In practice, the string tension is on the order of a giga, electron volt per femtometer. That number sounds abstract, so translate it. Separating quarks by a distance comparable to a proton's size costs enough energy to create new particles. That roughly linear detail matters because it changes what separation means. In electromagnetism, distance gives you relief because the field weakens and energy density drops. In QCD, distance becomes a cost that keeps accumulating, as if the vacuum charges rent by the femtometer. The farther you pull, the more energy you store, and the vacuum never offers a cheap escape route. This is why the strong force can feel eerie. Separation does not weaken the bond, it strengthens it. The vacuum between quarks does not become emptier, it becomes more energized, as if space itself is being wound tight. What looks like empty space is, in QCD, a structured medium with fluctuating fields. The nothing between quarks is busy, and it remembers the color charges at its ends. In the simplest cartoon, the flux tube has a nearly constant tension. Tension means energy per unit length, so every extra step apart stores more energy. The vacuum is not passive here. It behaves like a medium with structure, able to sustain a confined strand of field. If you could zoom in, the tube would flicker, because quantum fields never sit still. Yet the average behavior remains stubbornly string-like, and that stubbornness is confinement made visible. Confinement is the consequence, and it is not a mere experimental inconvenience. Isolated color charge is not observed, because the theory does not allow a lone colored object to become a free, long-lived particle. The only stable, observable states are color-neutral combinations, where the net color cancels. The rule is not that quarks are hidden, but that the spectrum of allowed particles excludes isolated color. Nature does not merely conceal quarks, it refuses to let them exist as solitary objects. Color neutrality is not about hiding something behind a curtain. It is more like a rule for what the vacuum will tolerate as an independent object. If you try to create a lone color source, the field responds so violently that it reorganizes the situation into neutral composites. The vacuum acts like a strict accountant, balancing color charge the way circuits balance current. When the books do not close, the system reshapes itself until they do. Baryons are one route to neutrality. 3 quarks combine so red, green, and blue sum to a colorless state, and that is the structure of protons and neutrons. Mesons are the other route, where a quark pairs with an antiquark of matching anticolor. In both cases, the colors combine into a singlet, which is the technical word for colorless. The hadron can still carry electric charge, spin, and mass, but it carries no net color that can leak outward. These combinations are not arbitrary, and they are not aesthetic. They are the simplest ways to build a singlet state under the color symmetry, meaning the whole object is unchanged by color rotations. In plain language, the hadron becomes invisible to long-range color fields. That invisibility is why we can talk about protons as stable particles at all. Without singlets, the world would be a storm of unbound color, with no quiet matter to build from. Historically, this was not obvious at first glance. In the 1960s, quarks were proposed as a way to organize a growing zoo of hadrons, and many physicists treated them as mathematical bookkeeping. The eightfold way, built from symmetry patterns, hinted that something simpler was hiding underneath. Then, experiments in deep, inelastic scattering revealed point-like constituents inside the proton, and the bookkeeping began to look like reality. The later development of QCD turned quarks into dynamical actors, while also explaining why they never appear alone. The flux tube picture also explains why trying to extract a quark backfires. If you inject energy to pull quarks apart, you do not get a lonely quark at the end. You get a longer tube and a larger reservoir of field energy trapped between the would-be separated charges. The field does not let you peel a quark away like a bead on a wire. It makes the attempt expensive, and then it pays that expense in a way you might not expect. Imagine a slow-motion shot inside a proton, rendered as a storm of shimmering lines. As you tug one quark away, the lines do not fade into emptiness. They tighten into a bright filament, like a glowing cable being stretched across a dark stage. The filament quivers as though it is alive, because it is made of a quantum field. The longer it gets, the brighter it becomes, as energy piles into the confined region. At some point, the tube stores enough energy that a different outcome becomes cheaper. The vacuum can produce a quark and antiquark pair, because energy can become mass through E equals mc squared. The string does not break by snapping into nothing, it breaks by making new matter. The process is often described as string breaking, but the phrase hides the key point. The vacuum supplies the possibility, and the injected energy supplies the payment. This is not magic, and it is not a violation of conservation laws. The energy you poured into the system becomes the rest, mass, and motion of new particles, while quantum fluctuations provide the root. In QCD, the vacuum is not empty. It is a restless ground state with permitted excitations. Virtual quark-antiquark pairs flicker into existence on short timescales, and the strong field can promote that flicker into a real, lasting pair. The result is a rearrangement that restores color neutrality without ever letting a lone color charge escape. The result is not one free quark, but two color-neutral hadrons. The original quark binds with the new antiquark, and the original partner binds with the new quark. The attempt to isolate a fraction of charge becomes an act of hadron production. In a high-energy collision, this happens repeatedly, producing a chain of hadrons rather than a single, clean fragment. The vacuum becomes a factory line, turning stretched field energy into composite particles. If you could see the event in a detector-like visualization, the single stretched tube would pinch and brighten. Then it would pop into two tubes, each shorter and calmer, because each ends on a neutral combination. The universe pays its energy debt by minting new composite objects. In the visual language of modern experiments, that minting becomes a spray of tracks. The tracks curve in magnetic fields, and their curvature quietly reveals their momenta and charges. This is why detectors see jets rather than free quarks. The hard scattering can kick a quark or gluon, but the color field then fragments into hadrons as it tries to neutralize itself. The final state is always a spray of colorless particles, carrying the direction of the invisible parton. In the data, a jet is not a single line, but a clustered pattern of energy deposits and tracks. It is a signature written in many small pieces, because confinement forces the story to be told indirectly. A jet is a kind of fossil record of confinement. You do not see the quark, yet you see the aftermath of its attempted escape. Dozens of hadrons, tightly collimated, arriving in patterns that encode the original momentum. The quark's track is replaced by a cascade of allowed end products. The jet is also a reminder that QCD is predictive even when it is messy. Statistical patterns, like how jets broaden and how energy is shared, match the theory's expectations. Confinement sounds absolute, yet QCD also contains its opposite behavior. At very short distances, quarks behave almost free. This is asymptotic freedom, and it is not a loophole because it is the other face of the same theory. The same gluon self-interactions that confine at long range also reshape the coupling at short range. QCD is not two theories stitched together. It is one framework with scale-dependent behavior. Asymptotic freedom means the effective strong coupling decreases as the momentum scale increases. When quarks are very close, the color charge is screened by gluon dynamics in a way that weakens the interaction. The proton can look like a set of quasi-free constituents during an ultra-fast high-energy hit. In technical terms, The coupling runs with energy, and the beta function of QCD is negative. That sign is the mathematical fingerprint of asymptotic freedom. The phrase effective coupling matters because the strength is not a fixed number. In quantum field theory, the vacuum polarizes, and virtual particles dress the bare charges. In QCD, that dressing works in an unusual direction because gluons contribute with the opposite sign compared to simple charge screening. In electromagnetism, vacuum polarization tends to screen charge, making it look smaller at long distance. In QCD, gluon self-interactions produce an anti-screening effect, making the interaction weaker at short distance and stronger as you step outward. In plain terms, the strong force thins out at short range. If you probe a proton with a very high-energy electron, the interaction happens so quickly and at such small distances that quarks act like independent targets. The proton becomes less like a solid sphere and more like a buzzing cloud of partons. Parton is a deliberately humble word because at high energies, you do not see tidy constituent quarks alone. You see quarks, antiquarks, and gluons sharing momentum in a shifting, probabilistic way. At larger separations, the coupling grows and the flux tube picture becomes accurate. The strong force is weak when probed at tiny distances, and strong when you try to separate charges to hadronic distances. The same equations produce both behaviors, depending on scale. This is why QCD is simultaneously calculable and stubborn. It gives you clean predictions at high energies, and then it turns nonlinear and confining where everyday matter is built. This scale dependence is why the strong force earns its confusing name. It is strong in the regime that builds protons and nuclei, where confinement dominates. It is comparatively weak in the regime that lets perturbative calculations work, where quarks act nearly free. The name strong is historically anchored in nuclear physics, where the force had to overpower electromagnetic repulsion inside nuclei. Yet the deeper story is that the coupling is not a single dial. It is a dial that moves with the question you ask. There is a historical twist hidden in that statement. The discovery of asymptotic freedom in the early 1970s made QCD credible as the theory of the strong interaction, because it explained why quarks looked free in deep, inelastic scattering. The same theory then insisted that those quarks could never be extracted, even in principle. This was a rare moment when theory and experiment met in a paradox that resolved into a deeper unity. Quarks behave free when struck hard, yet they remain bound when you try to carry them away. So, the story splits into two strong forces that share a name but not a level. The fundamental strong interaction is QCD, acting between quarks and gluons through color. The nuclear force that binds nuclei is residual, emerging from color-neutral protons and neutrons. That residual force is not a separate fundamental interaction. It is what's left over when confined objects, each neutral overall, still have internal structure that can be distorted. Residual nuclear binding is like molecular binding compared to electromagnetism. Atoms are neutral, yet they attract through leftover electromagnetic effects, because electrons and nuclei polarize. Nucleons are color neutral, yet they attract through leftover QCD effects, because their internal color fields can still distort. The analogy is imperfect, but it carries the essential idea. Neutrality does not mean featureless, and structure can create short-range forces even when the net charge cancels. In a nucleus, protons and neutrons are not point particles sitting politely apart. They are extended, dynamic objects whose internal quarks and gluons can be tugged slightly out of symmetry by a neighbor. That distortion creates an effective attraction at short range, even though net color cannot escape. The force is also saturating, meaning each nucleon mostly interacts with its nearest neighbors rather than the whole nucleus at once. That saturation is one reason nuclei have finite sizes and do not collapse into a single dense lump under residual attraction. In practice, that residual force is often described through pion exchange. Pions are mesons, quark-antiquark states, and they act as the effective carriers of the nuclear force at low energies. The nucleus is held together by an emergent interaction, not by direct long-range color. Historically, this picture traces back to Hideki Yukawa's proposal of a meson-mediated force long before QCD was written down. The pion, discovered later, fit the role as the lightest meson, and its lightness gives it the longest reach among hadronic messengers. If you visualize this, do not imagine a single gluon traveling between two nucleons across the nucleus. Instead, picture two neutral droplets close enough that their surfaces ripple, and a light meson field passes between them. The pion is not the fundamental messenger of QCD, yet it is the practical messenger of nuclei. The exchange is not a tiny ball thrown across space, but a quantum process that correlates the nucleon's internal states. The residual force is the shadow of color dynamics, softened and filtered through confinement. This distinction matters for the central question because it prevents a common confusion. Confinement is about color, and color does not leak far outside hadrons. Nuclear binding is what remains after confinement has already done its job, leaving composite objects that can still tug on each other. When we say strong nuclear force in everyday speech, we often mean the residual force in nuclei. When we say it in particle physics, we mean QCD itself, the deeper rule that makes nucleons possible. QCD also reframes what mass means in ordinary matter. The quarks inside a proton have small rest masses, only a few MeV each for up and down. Add those bare masses, and you do not get anywhere near the proton's 938 MeV. The gap is enormous, and it is telling you something profound. Mass is not only a property of ingredients, it can be a property of motion, fields, and binding when those forms of energy are trapped in a stable pattern. That mismatch is not a rounding error, and it is not a missing ingredient in the quark list. It is a statement about energy stored in motion and fields, trapped in a stable configuration. The proton is not a bag of heavy things. It is a bound state whose mass is mostly binding energy made tangible. In relativistic quantum mechanics, confining a particle to a small region forces large momenta, and large momenta mean large kinetic energy. QCD confinement makes that confinement unavoidable, so the energy cannot simply drain away. Most of the proton's mass comes from energy trapped by confinement. It comes from the kinetic energy of quarks moving relativistically inside the bound state. It comes from energy stored in gluon fields, and from the restless creation and annihilation of quark-antiquark pairs in the sea. Even the gluons, though massless as fundamental quanta, contribute energy through their field configurations. The proton's mass is an emergent property of a many-body quantum system, and emergence here is literal because the whole weighs far more than the sum of bare parts. The C is an important phrase because it reminds us that a proton is not just three quarks. Quantum fluctuations continually produce short-lived quark, antiquark pairs, and extra gluons, which share momentum and spin in complicated ways. The proton is a dynamic many-body system, even when it sits still. Deep inside, momentum is constantly traded, and color is constantly exchanged, yet the overall object remains stable. Stability in QCD is not stillness. It is a steady pattern of motion that does not unwind. Einstein's relation is not a slogan here. It is the accounting system. If the strong field stores energy, that energy gravitates and weighs and resists acceleration. The weight of your body is largely the energy of confined QCD, stabilized into protons and neutrons. It is a strange intimacy with the early universe. Every kilogram of ordinary matter is, in large part, the afterimage of confinement doing its work. This is the mass paradox that makes the strong force feel like a manufacturing rule. The universe does not merely contain matter, it converts field energy into the mass of stable hadrons. Confinement is a mass engine, running quietly inside every nucleus. It is also a reminder that empty space is not empty, because the vacuum structure is what allows confinement to store energy in the first place. If the vacuum were truly featureless, there would be no place for a flux tube to live. Pause on that thought, because it is easy to miss its strangeness. When you hold a rock, you are holding organized energy, and most of that energy is not electromagnetic. It is the energy of quarks and gluons, locked into patterns that cannot unwind into free color. The rock feels solid and classical, yet its mass is a quantum bookkeeping result. What other everyday properties are quietly built from rules we cannot see? Yet, QCD is also a theory that resists easy testing in the regime where it matters most. At short distances, we can calculate, because asymptotic freedom makes perturbation theory reliable. At hadron scales, we often cannot calculate cleanly, because the coupling is strong and the field is nonlinear. The same nonlinearity that creates flux tubes also blocks our usual analytic shortcuts. We can write the equations, but solving them exactly is another kind of challenge. Nonlinear means the field talks to itself, and that self-talk is loud. Small changes in one part of the gluon field can feed back into others, and the usual expansion tricks fail. The theory remains well-defined, yet our tools become blunt, so we lean on numerical methods and indirect signatures. This is where the language of effective theories becomes practical, because we often describe low-energy QCD in terms of hadrons rather than quarks. It is not surrender, it is choosing the right level of description for a strongly coupled world. So the evidence must be indirect and cumulative. We test QCD through jets and scaling violations, through hadron spectra and lattice simulations, through the way quark and gluon distributions evolve with energy. We test it by watching how confinement shapes what can exist as a free particle. We also test it by precision, because QCD corrections subtly shift rates and angular patterns in collider events. The theory leaves fingerprints even when it refuses to show us the culprit directly. Lattice QCD is one of the most striking bridges between equation and matter. Space and time are approximated as a grid, and the theory is simulated numerically, letting confinement and hadron masses emerge from first principles. The results are not perfect, yet they are persuasive, because the patterns match what nature displays. In a lattice calculation, the gluon field lives on links between grid points, and quark fields live on the points themselves. As the simulation runs, confinement appears not as an assumption, but as an outcome, with flux tube-like behavior and realistic hadron masses. But a deeper test tempts us, because QCD predicts more than confinement inside cold protons. It predicts that under extreme temperature or density, confinement can weaken. The flux tubes can dissolve, and quarks and gluons can roam in a new phase. This is not the disappearance of color, but a change in how color is screened by the medium. The vacuum becomes something else, and the rules of what counts as a stable object shift with it. This is not a minor adjustment, because it changes what the vacuum prefers. The same degrees of freedom exist, yet the environment reshapes their behavior, like ice becoming water, without changing the atoms. In the hot phase, color is still there, but it is no longer locked into hadronic boundaries. The medium can screen color over short distances, so the energy cost of separating charges changes dramatically. Instead of a long, stubborn string, the field becomes more like a crowded plasma, where influences are quickly damped. That possibility raises the next tension in our story. If confinement is a rule, can we ever reach conditions where the rule loosens? Can we create matter where color is not locked into hadrons, even if only for an instant? And if we do, how would we recognize it, given that the final products must still be colorless? The challenge is almost philosophical. We are looking for a phase that cannot be photographed directly, only inferred from what it leaves behind. The only known path is to recreate the early universe's conditions. In the first microseconds after the Big Bang, the cosmos was too hot for hadrons to exist as stable bound states. Quarks and gluons formed a quark-gluon plasma, and confinement emerged only as the universe cooled. There is a quiet audacity in that claim, because it says the matter around you is not the default state of QCD. Ordinary hadrons are the cooled, condensed phase of a hotter, freer beginning. Picture that early universe not as a starry sky, but as a near-uniform furnace. There are no atoms, no nuclei, and no protons with familiar edges, only a dense, seething medium where quarks and gluons constantly exchange color. Then expansion cools the fire, and hadrons condense as a new kind of stability. If we could watch it, we might see a transition from a fog of free color to droplets of confinement. The universe would look less like a collection of objects and more like a continuous fluid, gradually learning the concept of particles. To see quarks and gluons unshackled briefly, we must build that heat again. We must collide heavy nuclei at enormous energies and read the aftermath through the hadrons that finally emerge. The next chapter begins where confinement might melt and where QCD becomes a laboratory for the first moments of time. In those collisions, the detectors become our eyes, and statistical patterns become our language. We will not see the plasma directly, but we may see how it flows, how it cools, and how it reshapes jets that try to cross it. And when we attempt it, we will still face the same irony. Even if a quark-gluon plasma forms, it will not arrive with labels, and it will not linger. It will cool, hadronize, and leave only traces, patterns in jets, flows, and yields that we must learn to interpret. The story ends the way it began, with a rule that hides its mechanism in plain sight. We name the theory, we write the equations, and then we chase the consequences through the only things the universe allows us to hold. The proton has been our laboratory, but it is also a fossil from the beginning, carrying a record of forces that once ruled everywhere. If confinement is a rule, then the early universe tests when that rule can fail. Wind the clock back past atoms, past nuclei, past any stable hadron you could name, and even past the idea of particles as we picture them now. In the first microseconds after the Big Bang, temperature and density were so extreme that ordinary matter could not exist in any durable form. The numbers are hard to hold in the mind, so we translate them into physical consequences. Thermal energies were comparable to hundreds of mega. Electron volts, meaning random motion could rip apart would-be bound states almost as quickly as they formed. The universe was not a place for chemistry, and it was barely a place for nuclei. There were no atoms because electrons could not bind to anything for long, not with photons and charged particles constantly kicking them free. The electromagnetic plasma was so energetic that any nascent atom was immediately ionized again, as if the cosmos were permanently striking the reset button. Even the language of orbitals and shells simply did not apply. There were no nuclei because protons and neutrons were not yet stable objects, at least not in the way we mean today. The strong interaction was present, but the environment was so hot that the usual nuclear binding energies were trivial by comparison. A nucleus requires not only strong forces, but also calm enough conditions to let those forces organize matter. And even the idea of a proton as a persistent bound state was not guaranteed, because confinement is not a switch you flip by decree. A proton is a particular solution of quantum chromodynamics, and solutions can change when temperature and density change. In that earliest era, the universe was asking QCD a different question than the one we ask in a quiet laboratory. The universe was a hot, dense medium of quantum fields in rapid equilibrium, more like a seething ocean than a collection of separate objects. Quark fields, gluon fields, electron fields, photon fields, all of them were excited, interacting, and continually exchanging energy. The word equilibrium here does not mean stillness. It means the chaos had statistical rules. Energy dominated everything, and the expansion rate set a relentless cooling schedule that no interaction could negotiate with. Space itself was stretching, and as it stretched, the typical energy per particle fell. What mattered was not chemistry or structure, but which phases of QCD were possible at each temperature. At sufficiently high temperature, QCD predicts deconfinement, a change in how color charge behaves in bulk matter. Color is still a charge, and quarks and gluons still feel it, but it is no longer locked into isolated hadrons. The relevant degrees of freedom become quarks and gluons moving through a shared medium. This is the quark-gluon plasma, or QGP, the quark soup of cosmic dawn, and the name can mislead if we imagine a thin vapor. It is not a gas of free particles drifting independently in empty space. It behaves as a strongly interacting fluid with collective motion and remarkably short, mean free paths. In modern language, we would say the plasma is close to a perfect fluid, one with very low viscosity compared to its entropy density. That phrase sounds abstract, so picture what it implies. Disturbances do not simply dissipate into randomness, they propagate as coordinated flow. The medium responds like a liquid, not like a swarm. In a QGP, quarks and gluons exchange color constantly, and the medium screens color over short distances. Much like electric charges are screened in an ordinary plasma, The long flux tubes that enforce confinement in cold matter cannot persist in the same way because the environment keeps rearranging the field lines. The cost of separating color charges changes because the medium itself reorganizes the vacuum. A useful image is to imagine trying to pull two magnets apart while submerged in a churning, conductive fluid that keeps short-circuiting the field between them. In the vacuum of today, QCD flux tubes behave like stretched strings that resist separation. In the early universe's hot bath, those strings are disrupted before they can stabilize. This is the first major shift in our story's setting and scale, because the same QCD that traps quarks inside a proton also governs the entire universe. There is a strange symmetry here. Microscopic rules become cosmology when the cosmos is small enough. For a brief time, the universe itself was the Hadron Collider. The timeline is brief, but the stakes are permanent, because what freezes out in these moments becomes the inventory for everything later. Within microseconds, expansion cools the plasma through the QCD transition region, where the character of matter changes rapidly. The question is not whether QCD changes, but how the change happens. In QCD, phase transition can mean different things depending on conditions, and the early universe occupies a specific corner of that map, at low baryon density, which is relevant for a universe with only a tiny matter excess. The transition is expected to be a crossover rather than a sharp first-order jump. That means there is no single boiling point, but a temperature range where the medium's properties shift quickly. A crossover matters because it leaves fewer dramatic relics, at least in the obvious sense. A first-order transition can produce bubbles, latent heat, and violent discontinuities, like water snapping into steam. A crossover is smoother, yet it still reshapes the behavior of the strong force in bulk, and it still decides what objects can persist. As cooling continues, confinement reasserts itself, not as a new law, but as the vacuum returning to its familiar low-temperature structure. Color must again be hidden inside color-neutral combinations that can survive as independent particles. The universe begins to trade a fluid of quarks and gluons for a gas of hadrons. Hadronization is that trade, and it is a manufacturing step rather than a footnote, because it converts a continuous medium into a catalog of particles. Quarks and gluons reorganize into mesons and baryons because those are the allowed long-lived states under confinement. The spectrum of what can exist narrows into familiar building blocks. In the plasma, quarks are not free in the everyday sense, but they are not trapped inside individual protons either. They move through a collective environment where interactions are constant and distances are short. During hadronization, those same quarks must find partners, 2 for a meson, 3 for a baryon, and lock into a color-neutral combination. This locking is not a gentle settling, because the strong interaction does not fade politely. It is a reorganization of fields, a reshaping of correlations, and a redistribution of energy into bound structures. If you could watch it, you would not see neat assembly lines. You would see a turbulent medium freezing into countless droplets of identity. Protons and neutrons emerge as stable baryons once the temperature drops enough for bound states to survive the surrounding noise. Their internal quarks are still never alone, but now the bound states are robust against thermal breakup. Confinement becomes the rule that turns a plasma into particles. This is where the documentary's central question widens into cosmology, because the early universe forces us to separate two ideas we often blend. A quark cannot be observed alone in our detectors because confinement forbids isolated color in the vacuum we inhabit. In the early universe, quarks still could not be isolated as naked color charges. Yet they were not confined into individual hadrons either. The difference is the medium, and the medium is not a minor detail. It is the stage that changes the play. In a hot plasma, color is screened by the presence of many charges, and the effective behavior of the vacuum is altered by temperature. Confinement is not erased, but the conditions that make long flux tubes stable are no longer present. Cooling changes the vacuum's effective behavior, and the medium stops being able to screen color efficiently over the relevant distances. The same field that once flowed collectively begins to lock itself into localized color-neutral lumps. The universe condenses into hadrons the way a fluid condenses into droplets, except the droplets are protons, pions, and neutrons. That condensation is essential for everything that comes later, because later chapters require durable inputs, not a shapeless medium. Big Bang. Nucleosynthesis requires protons and neutrons as starting materials. Without hadronization, there is no inventory of nucleons to fuse into light nuclei minutes later. It is easy to say minutes later and forget how enormous that gap is on this early timeline. Microseconds to minutes is an eternity in an expanding universe, long enough for temperatures to fall by orders of magnitude. The QCD transition is the moment when the universe first acquires stable hadronic building blocks. Hadronization also reframes the origin of mass in the visible universe because it reveals where most of that mass actually comes from. The bare masses of up and down quarks are small, only a few MeV, and they cannot account for the roughly 938 MeV mass of a proton. When confinement sets in, energy stored in quark motion, gluon fields, and the dynamics of the strong interaction becomes the rest mass of hadrons. This is not metaphorical conversion. It is literal bookkeeping under E equals mc squared, and the ledger is kept by QCD. The cooling universe does not just lose heat, it reorganizes energy into stable mass. The mass budget of ordinary matter is largely the frozen energy of confined fields. If you want a more concrete picture, imagine the proton as a tiny, restless system where quarks dart and gluons constantly exchange momentum. The mass is not a pile of heavy ingredients. It is the energy of motion and binding in a confined space. Confinement is the mechanism that makes that energy count as a persistent object. So, the early universe is not only a place where confinement fails, at least in the sense of deconfinement in bulk matter. It is also the place where confinement turns on, and where most visible mass is minted in a form that can endure. The rule that forbids a lone quark becomes a cosmic mass engine. There is historical weight behind this idea, because it took decades to accept that most mass is not fundamental mass. The development of QCD in the 1970s and the recognition of asymptotic freedom clarified why quarks behave almost free at high energies, yet remain confined at low energies. The early universe, unknowingly, was the ultimate high-energy experiment. Yet confinement is not the whole story of why anything exists to confine, and this is where the mystery deepens. The early universe should have produced matter and antimatter in nearly equal amounts, because high-energy processes tend to create particle. antiparticle pairs symmetrically. If that symmetry were perfect, annihilation would leave almost nothing behind, just radiation and a thin residue. Some process tipped the balance, leaving a small excess of baryons over antibaryons, roughly a few parts in 10 billion. We call the general problem baryogenesis, and we still do not fully know how nature did it. Confinement cannot explain the imbalance, but it determines what the surviving imbalance becomes. This distinction matters because it separates origin from outcome. Baryogenesis sets the tiny numerical advantage, but hadronization decides the form that advantage takes as the universe cools. A small excess of quarks becomes a universe filled with protons, neutrons, and eventually atoms. Once hadronization occurs, the remaining quarks are locked into protons and neutrons rather than drifting as a plasma. Antiprotons and antineutrons also form from antiquarks, and annihilation continues as long as temperatures allow and densities remain high. The universe cools into a state where the leftover baryon excess becomes durable matter. Annihilation is not a single event, but a drawn-out thinning, like fog burning off as the day warms. Except here, the fog is antimatter disappearing into photons. Each annihilation converts mass back into radiation, feeding the photon bath that will later dominate the universe's energy density. The survivors are few, but they are enough. From there, the next milestones are timed by expansion and by binding energies, because binding energies act like thresholds. Minutes later, during Big Bang nucleosynthesis, protons and neutrons fuse into light nuclei like deuterium and helium with traces of lithium. The universe is still too hot for complex nuclei, but it is finally cool enough for the first nuclear chemistry. Much later, at recombination, electrons bind to nuclei, and atoms finally become stable, because the photon bath has cooled enough to stop ionizing everything. This is when the universe becomes transparent, allowing light to travel long distances without constant scattering. The cosmic microwave background is the afterglow of that moment. Those later chapters of cosmic structure depend on this earlier one, and the dependency is absolute rather than optional. Without the QCD transition and hadronization, there are no nucleons to fuse and no nuclei to capture electrons. The cosmic story of galaxies begins with a microscopic rule about color. This chapter also loops back to the proton in your hand, because the proton is not merely a common particle. Every proton today is a cooled remnant of that transition, still enforcing confinement internally, still storing most of its mass as field energy. The universe's earliest phase is gone, but its outcome is everywhere. There is tension in that statement, because it sounds like a closed history with no way to check the details. If the quark soup existed only once, then it is forever beyond direct study, sealed behind the horizon of time. We would be stuck inferring it from theory, from cosmic leftovers, and from the mathematical consistency of QCD. But QCD offers a loophole that is not a violation, and it comes from the very idea of phases. If temperature and density control confinement, then extreme conditions can resurrect the deconfined phase. The early universe can be replayed briefly in a laboratory. The thought is almost audacious when stated plainly, because it asks us to imitate the first microseconds with human-made machines. Can we make quark soup on Earth and watch confinement fail in real time, at least in the collective sense? Can we create a droplet of QGP, let it expand, and read its properties from the hadrons it becomes? can we test the same physics that once governed the whole universe, even though our version will be microscopic and short-lived? Can we learn about screening, viscosity, and the approach to confinement by studying the debris of a fireball? And can we do it without ever seeing a lone quark, because confinement still forbids that final, simple image? This is where the story turns from cosmic history to modern machines, and the change in scale is itself a kind of drama. The next step is to collide heavy nuclei at ultra-relativistic energies and create a tiny, short-lived fireball. The goal is not to see free quarks, but to see a medium where confinement is weakened and collective behavior emerges. In practice, that means accelerating ions, lead at the Large Hadron Collider, gold at other facilities, until they are flattened by Lorentz contraction into near pancakes of energy. When they collide, the energy density spikes, and for an instant the conditions resemble those early microseconds. The fireball expands, cools, and hadronizes, echoing the universe's own sequence on a miniature clock. Transition. The cosmic plasma is long gone, unless we can recreate it. We move from the first microseconds to the Large Hadron Collider, where heavy ion experiments briefly resurrect the primordial state. In that arena, confinement still wins in the end, because detectors only see hadrons that survive long enough to reach the instruments. The evidence must come from patterns, elliptic flow, correlations, and jets that emerge weakened after crossing the medium. The universe still refuses to show a lone quark, even when we remake its earliest phase. That refusal is the point, because it forces us to become indirect and therefore more precise. We infer a deconfined medium from how it pushes on particles, how it redistributes energy, and how it modifies the passage of fast partons. The QGP is recognized not by a photograph, but by a signature written into motion. And the deeper irony is that the same rule that hides quarks also manufactures matter, first in the cosmos, and now inside every proton. Confinement is both a veil and an engine, both a limitation on observation and a mechanism of creation. The next chapter asks how we recognize a plasma we cannot photograph, and how we measure a phase where confinement loosens without ever disappearing. Expanded section continues. To appreciate why this matters, it helps to linger on the visual logic of the early universe, because it is unlike any familiar scene. Imagine a darkness that is not empty, but saturated. Every cubic centimeter packed with energy, every direction filled with scattering and exchange. There is no surface to look at, only a volume where fields fluctuate and relax again and again. In that volume, temperature is not a weather report, it is a measure of typical particle energies, and those energies set the rules of survival. Bound states are only meaningful when the environment cannot instantly disrupt them. In the first microseconds, disruption was the default. The expansion of space provides the cooling, and it does so without friction, without a wall, and without a thermostat. As the universe grows, wavelengths stretch, momenta redshift, and the average energy per degree of freedom drops. The cosmos is doing thermodynamics on itself. QCD, in turn, is doing something subtle because its coupling depends on scale. At short distances and high energies, quarks interact more weakly, a property called asymptotic freedom. At larger distances and lower energies, the interaction strengthens, and confinement becomes unavoidable. That running of the coupling is why hotter can mean less confined, even though the strong force is still present. In the early universe, typical energies were high enough that quarks and gluons could roam within the medium, exchanging color rapidly. The plasma is not non-interacting, it is interacting in a different regime. The phrase "degrees of freedom" is a technical one, but it has a simple meaning here. It asks what the universe can effectively use as its building blocks at a given temperature. In the QGP, the building blocks are quarks and gluons. After hadronization, the building blocks are hadrons. This change affects the universe's thermodynamic properties, including how pressure relates to energy density. It also influences how quickly the system cools, because the number of active degrees of freedom determines how energy is shared. Even without a sharp phase boundary, the crossover region is a thermodynamic turning point. When we say the transition is a crossover at low baryon density, we are summarizing an entire program of theoretical work. Lattice QCD, which simulates the theory on a discretized space-time grid, suggests a smooth but rapid change around a characteristic temperature near 150 to 170 MeV. That corresponds to trillions of degrees in everyday units, though the number is more symbol than intuition. The early universe's baryon density was low in a specific sense, because the net baryon number was tiny compared to the number of photons. There were vast numbers of quark-antiquark pairs, but only a slight excess of quarks that would eventually become matter. That is why the early universe follows the low-density path through the QCD phase diagram. The word diagram might suggest a tidy map, but the reality is a landscape with uncertainties. Different regions may host different kinds of transitions, and at higher baryon densities, the story could include a critical point. The early universe, however, appears to have taken the smoother road, leaving fewer obvious scars. Still, even a smooth road can reshape everything it touches. As the plasma cools, screening lengths change, correlations grow, and the medium's ability to support deconfined color fades. The system begins to prefer color-neutral combinations because they are the stable excitations of the low-temperature vacuum. In practical terms, that means quarks begin to feel the confinement scale again, not as a single moment, but as a tightening constraint. The environment no longer tolerates long-range color fields, and the energy cost of separation rises. Hadrons become the economical way to package color. The hadrons that form are not only protons and neutrons, and that is an important nuance. The early hadron gas would be rich in pions and other short-lived resonances, because the temperature is still high enough to populate many states. Most of those resonances decay quickly, leaving behind the more stable nucleons and a bath of lighter mesons. This is a universe that is still busy, still reactive, still full of collisions. Protons and neutrons are stable on these timescales, but they are not isolated. They are immersed in a hot hadron gas. The cosmos has not yet become the quiet, dilute expanse we know. The distinction between stable and abundant matters here, because stability alone does not guarantee survival. Abundance is controlled by equilibrium and freeze-out, by reaction rates compared to expansion. As the universe expands, reactions eventually become too slow to maintain equilibrium, and populations freeze into their later proportions. The QCD transition sets the stage for that freeze-out, because it determines which reactions are even possible. In a deconfined plasma, quark-antiquark creation and annihilation are common, and gluons freely participate. In a hadron gas, the relevant processes are hadronic scatterings and decays. So when we say the universe begins to trade a fluid of quarks and gluons for a gas of hadrons, we are describing a change in the universe's entire vocabulary of interactions. The actors remain quantum fields, but the roles they play become discrete and recognizable. The universe becomes legible in particle names. There is also a geometric intuition to confinement that becomes clearer in this cosmological setting. In the vacuum today, the color field between quarks is squeezed into a tube, and the energy grows roughly with separation. In a hot medium, the tube can be broken by pair creation and screened by other charges. That screening is often described with a dBi length, a distance beyond which a charge's influence is exponentially suppressed. In QGP, color dBi screening limits how far color fields extend before the medium neutralizes them. As the universe cools, that screening length changes and confinement becomes effective again. This is why the early universe can be deconfined without violating the principle that isolated color is not observed. The medium is full of charges, so color is always interacting and always being neutralized over short distances. Deconfinement is a collective property, not a permission slip for solitary quarks. The visual metaphor of soup is therefore more than poetic. In a soup, ingredients are present everywhere, and local structure is temporary, constantly stirred and remixed. In the QGP, quarks and gluons are everywhere in the medium, and any would-be hadron is like a brief eddy that dissolves. Then the stirring slows, not because anything chooses to slow, but because expansion reduces the energy available to keep everything mixed. The eddies last longer, correlations persist, and eventually the ingredients settle into stable combinations. The soup becomes a collection of droplets. Hadronization is sometimes described as freezing out, but that phrase can hide the complexity. The system is not freezing in place. It is transitioning from one set of excitations to another. It is a relabeling of what counts as a particle. In the early universe, this relabeling happens everywhere at once because the universe is homogeneous on large scales. There is no container wall, no cold surface where droplets first form. The entire cosmos cools together, and the transition is a global event. Yet global does not mean uniform at every microscopic point, because thermal fluctuations always exist. Small variations in density and temperature would have been present, and they could influence local timing. The universe is smooth, but it is never perfectly smooth. Those fluctuations are not the main driver of hadronization, but they remind us that the early universe is not a cartoon. It is a physical system with noise, with statistics, and with the constant interplay of expansion and interaction. The remarkable fact is not that it was messy, but that it produced such a consistent outcome. That outcome includes the protons that dominate ordinary matter today, and it includes their internal structure. A proton is not three quarks sitting still in a triangle, despite the simplicity of that picture. It is a dynamic bound state where gluons carry much of the momentum and where quark-antiquark pairs flicker in and out of existence. In QCD, the proton's properties emerge from this complexity, and confinement is the constraint that makes the complexity self-contained. The early universe provides the conditions under which that constraint was temporarily relaxed in bulk. It is a rare chance in principle to see QCD in both of its characteristic regimes. This is why the early universe is a test of the rule, not a refutation. Confinement is a property of the low-temperature vacuum, and the vacuum itself is not an unchanging stage. Temperature changes the effective vacuum, and therefore changes what confinement means in practice. The phrase effective vacuum can sound like wordplay, so anchor it in a simple idea. What we call empty space has properties, and those properties can change when space is filled with a hot medium. In the early universe, empty space was never truly empty. The QCD transition is therefore a change in the ground state of the theory under thermal conditions. It is the universe moving from one self-consistent arrangement of fields to another. The fact that it happens smoothly does not make it trivial. It makes it subtle. Subtle transitions can still have decisive consequences because they determine what survives as the universe cools further. Once hadrons exist as stable entities, the next question becomes their relative numbers and the neutron-to-proton ratio. That ratio, shaped by weak interactions and freeze-out, will later influence how much helium is produced. Our chapter does not need to follow every reaction in detail, but it must acknowledge the chain. Hadronization provides the nucleons, then weak processes shuffle neutrons and protons, then nucleosynthesis assembles light nuclei. Later, recombination builds atoms and gravity builds structure. So when we say, the cosmic story of galaxies begins with a microscopic rule about color, we are not being metaphorical. The existence of stable baryons is a prerequisite for everything that emits starlight. The first microseconds are the foundation of the visible universe. The mass story deepens when we remember that mass is not simply stuff. In relativity, mass is energy in a stable rest frame package. Confinement provides that package by trapping energy in a bound configuration. This is why the proton's mass is not mainly the sum of its quark masses. The quarks are light, but the binding dynamics are energetic. The gluon field contributes, the quark kinetic energy contributes, and the pressure of confinement contributes. In a sense, the proton is a stabilized storm, and its mass is the storm's energy measured at rest. The early universe minted countless such storms as it cooled. What looks like solid matter later is, at its core, organized field energy. This perspective also clarifies why the QCD transition is not merely a change in particle types. It is a change in how energy is stored and transported. In the plasma, energy is in a collective fluid. In the hadron gas, energy is carried by particles with rest mass. That shift influences how the universe's pressure evolves, and pressure influences expansion dynamics. The early universe is radiation-dominated, but the details of the equation of state still matter for precise cosmological calculations. QCD leaves fingerprints even when it does not leave dramatic relics. Now, return to the matter, antimatter tension, because it is the unresolved question that hovers over this entire era. If baryogenesis produced only a tiny asymmetry, then the early universe was still filled with matter and antimatter in enormous numbers. The QGP would have contained quarks and antiquarks in near balance. As hadronization proceeds, that balance becomes packaged into baryons and antibaryons, mesons and antimesons. Annihilation then becomes a competition between reaction rates and expansion. As the universe dilutes and cools, annihilations become less frequent, and the small excess remains. The photons produced by annihilation join the radiation bath, and that bath will later become the cosmic microwave background. In that sense, the glow of the universe carries the memory of annihilation, even if it does not reveal the detailed mechanism of baryogenesis. The absence of antimatter is written into the presence of light. It is worth pausing on the scale of the asymmetry, because it is both tiny and decisive. For every roughly 10 billion antibaryons, there were about 10 billion and 1 baryons. After annihilation, that 1 is what remains to build stars, planets, and observers. Confinement did not create that 1, but it ensured that the 1 became protons and neutrons rather than a lingering quark fluid. The asymmetry needed a container, and hadrons were the containers available. The universe's matter is not only an excess, it is an excess in a particular form. From the standpoint of visual narration, you can imagine the universe cooling through the QCD crossover as a gradual sharpening. Before, everything is a blur of fields and charges with no stable edges. After, the blur resolves into distinct packets, hadrons, still colliding, still hot, but now countable. Those packets then become the ingredients for the next act, where nuclear binding energies start to matter. Deuterium, for example, is fragile, and it cannot survive until the universe cools enough that photons stop breaking it apart. That is why nucleosynthesis waits, even after protons and neutrons exist. This waiting illustrates a general principle of early cosmology. The universe often has the right ingredients before it has the right conditions. Hadronization supplies nucleons early, but nuclear assembly must wait for a later thermal threshold. Recombination is another example of the same logic. Nuclei exist long before electrons can bind, because the photon bath remains energetic enough to ionize atoms. Only when the universe expands and cools sufficiently do atoms become stable and the cosmos becomes transparent. So our chapter sits at the beginning of a chain of thresholds, each set by the competition between binding energies and thermal agitation. QCD sets the first threshold for ordinary matter because it determines when quarks become hadrons. Everything else is downstream. Now, the story's tension returns because this entire early phase is absent from direct astronomical observation. We do not see the QGP directly in the sky, and we do not have photons from the first microseconds traveling freely to us. The universe was too opaque, too dense, and too interactive. That opacity is not a failure of our instruments. It is a physical fact. Photons scattered constantly, and any would-be signal was thermalized into the bath. The early universe hides itself behind its own equilibrium. So we rely on theory, on consistency, and on indirect evidence, and that can feel unsatisfying. Yet physics has a way of turning indirectness into strength, because indirect signatures can be quantified. If we can recreate the conditions, we can measure the properties. This is why the laboratory loophole matters so much, and why it is not merely a technological boast. Heavy ion collisions are our attempt to produce a controlled, repeatable version of the QGP. They let us vary energy, system size, and geometry, and then read the outcome. The conceptual move is bold, but straightforward. If the early universe was hot enough to deconfine quarks and gluons, then a sufficiently energetic collision can do the same in a tiny region. The region will be short-lived, but it will be real. In a collider, the time scales are astonishingly short, measured in femtoseconds, yet the physics is the same kind of physics. The fireball forms, thermalizes to some degree, expands hydrodynamically, and then hadronizes. The sequence echoes cosmology, compressed into a subatomic flash. The Large Hadron Collider, with its heavy ion program, is one of the places where this flash is engineered. Lead nuclei are accelerated to near light speed, and their collisions create energy densities high enough to cross into the deconfined regime. The detectors then record the hadrons that emerge after the medium cools. The key challenge is that we cannot hold the plasma still and examine it like a sample in a jar. We must infer its properties from the final state particles, and we must separate medium effects from the initial collision geometry. This is why patterns like collective flow are so important. Collective flow is the imprint of pressure gradients, and pressure gradients are a property of a fluid. If the medium were a weakly interacting gas, particles would stream out with little coordination. If it is a strongly coupled fluid, the initial shape of the overlap region becomes a momentum space pattern. Jet quenching is another signature, and it is conceptually vivid. A high-energy quark, or gluon, produced early in the collision tries to escape as a jet of hadrons. If it passes through QGP, it loses energy, and the jet emerges dimmer and modified, like a beam of light passing through fog. These are not new topics for our story, but they are the modern echoes of the early universe's physics. They are the ways we see deconfinement without ever seeing a free quark. Confinement remains the final curtain, but the performance leaves traces. So, when we say the universe still refuses to show a lone quark, we are describing a constraint that shapes our entire method. The refusal forces us to become detectives, reading the medium from its effects. It turns the absence of direct images into a discipline of inference. And that discipline loops back into cosmology, because the better we understand QGP properties in the laboratory, the more confident we become about the early universe's behavior. We refine the equation of state, the screening behavior, and the dynamics of hadronization. We turn a vanished epoch into a testable chapter. The mood remains mysterious, because even with these tools, the early universe keeps some secrets. The exact nature of the crossover, the precise transport properties of QGP, and the full story of baryogenesis remain active frontiers. The first microseconds are not only history, they are still a question. Yet the narrative arc is clear. The proton in your hand is a relic of confinement, and the early universe was the one time confinement loosened its grip on bulk matter. The universe cooled, confinement returned, and mass took on durable form. Then, much later, light and structure followed. That is why the chapter ends with a promise rather than a conclusion. If we can create quark soup on Earth, then the first microseconds are not lost to time. They become an experiment. Transition. The cosmic plasma is long gone unless we can recreate it. We move from the first microseconds to the Large Hadron Collider, where heavy ion experiments briefly resurrect the primordial state. In that arena, confinement still wins in the end, because detectors only see hadrons, and the plasma itself vanishes before it can be photographed. The evidence must come from patterns, flows, and suppressed jets that cross the medium. The universe still refuses to show a lone quark, even when we remake its earliest phase. And that refusal is the point, because it ties the cosmic and the microscopic into one rule. The same rule that hides quarks also manufactures matter, first in the cosmos and now inside every proton. The next chapter asks how we recognize a plasma we cannot photograph, and how we measure a phase where confinement loosens without ever disappearing. The early universe is gone, but its conditions are not beyond reach, because physics leaves traces we can deliberately reproduce. If confinement depends on temperature and energy density, then a machine can test the boundary. The question is not whether we can visit that era, but whether we can force matter to briefly behave as it did. On screen, the modern world gives way to a buried circle of infrastructure, service tunnels, cryogenic pipes, and cable trays that vanish into the rock. The Large Hadron Collider is that machine, built as a ring of magnets and radio cavities. It accelerates charged particles close to light speed, then forces head-on collisions. The ring is enormous by human standards, yet it exists to interrogate distances smaller than an atomic nucleus. The LHC sits beneath the French-Swiss border, a technological descendant of earlier colliders that slowly climbed the energy ladder. Its tunnel once housed the LEP electron-positron collider, and that history matters because each generation taught physicists how to control beams with greater precision. Now the same underground circle is repurposed for protons and heavy ions, which are messier projectiles but vastly more energetic. The machine is not only large, it is cold. Superconducting magnets run near absolute zero, so they can bend beams that would otherwise fly straight. A proton at rest is familiar, but a proton in the LHC is a different object in practice. It becomes a tightly focused packet of probability, a moving bundle of quarks and gluons, whose internal motion is revealed only when struck. Radio frequency cavities provide the push, timed electric fields that repeatedly kick the beam forward. With each lap, energy accumulates, and the beam becomes more rigid, demanding stronger magnetic fields to steer it. Energy matters because it sets the resolving power of the probe. Higher momentum transfer means shorter distances, where quarks and gluons behave nearly free. This is a consequence of asymptotic freedom, the counterintuitive QCD fact that the strong force weakens at very short range. In plain terms, the closer you look, the less sticky quarks appear, until you step back and confinement snaps into place. The visuals can slow down to a simple metaphor, a camera zooming in until grain becomes structure, then structure becomes a blur of motion. In scattering, the zoom is set by the exchanged momentum, often written as Q. Large Q corresponds to small distances, and it is at large Q that perturbative calculations become reliable. That reliability is why proton collisions can be treated as a clean test of QCD at the hardest point of impact. A collider does not pry a quark out and hold it up to the light. It creates violent, brief interactions, then reads the aftermath that confinement permits. The interaction time is so short that it is measured in fractions of a femtometer, divided by the speed of light. Even if a quark is struck hard, it cannot drift away as a colored object, because the QCD vacuum does not allow color to remain exposed. That limitation is not a technical failure, and it is not a missing detector component. It is a rule built into the theory, and the LHC is designed to collide particles hard enough to test how that rule manifests. The machine creates conditions where quarks and gluons are produced abundantly, yet it forces us to infer them indirectly. This is the experimental art of high-energy physics, measuring what cannot persist by studying what must. In the LHC, two experimental modes share the same tunnel, but ask different questions. Proton-proton collisions map high-energy QCD, while heavy ions recreate bulk deconfinement. The switch between them is not cosmetic, because the beams differ in charge, mass, and the way they fill the accelerator. A lead nucleus carries many protons, so it is easier to accelerate in some respects, yet harder to keep stable at high intensity. Proton beams are the precision tool aimed at the hard scatter. Two partons collide inside two protons, and the event's core is calculable. Parton is a deliberately flexible word. Sometimes it means a quark, sometimes a gluon, and sometimes a C-quark that exists as a quantum fluctuation. The probability of finding a parton with a given momentum fraction is encoded in parton distribution functions, which are themselves measured and refined over decades. In a visual overlay, a proton becomes a flickering cloud, with quarks and gluons sharing momentum in a restless exchange. When two protons collide at high energy, it is rarely the whole protons that matter. It is usually one quark or gluon from each proton that undergoes the hardest interaction, while the rest becomes the underlying event, a softer spray that still carries information about QCD. The event is therefore layered, an intense core embedded in a broader, noisier context. Yet even here, the central rule remains unbroken. The outgoing quark, or gluon, cannot travel as an isolated particle because color cannot remain exposed. The reason is not that the quark is heavy or slow, but that the color field between colored objects does not spread out like an electric field. In QCD, the field lines squeeze into a flux tube, a narrow region of energy that resists being stretched. Instead, the parton pulls a color field behind it, and the field fragments. The energy becomes new quark pairs, and the final state becomes hadrons. As the parton tries to separate from its color partners, the energy stored in the flux tube grows, until it becomes energetically favorable to create a quark-antiquark pair from the vacuum. The string breaks, then breaks again, and the process continues until only color-neutral combinations remain. Detectors never record a quark track, because there is no quark track to record. They record charged hadrons curving in magnetic fields, plus neutral energy deposits. In the detector's inner layers, silicon sensors register tiny bursts of charge as particles pass through, leaving a sequence of points that can be fit into a helix. Farther out, calorimeters absorb particles and measure their energy, converting showers of secondary interactions into measurable signals. The camera can drift through a detector cross-section, revealing a cathedral of concentric instruments, tracking layers, electromagnetic calorimeters, hadronic calorimeters, and muon chambers. Each layer is built from different materials because different particles interact differently with matter. Electrons and photons shower quickly, while hadrons penetrate deeper and break apart in more complex cascades. Muons, by contrast, are penetrating and leave clean tracks in outer chambers, like signatures written at the edge of the machine. From those deposits, experiments reconstruct jets, narrow sprays that point back to the original parton. A jet is confinement's compromise, a directional memory written in many particles. The reconstruction is algorithmic and statistical because the detector sees individual hits and energy clusters, not a pre-labeled jet. Jet algorithms gather nearby energy into a cone-like structure, and then corrections account for detector response and the underlying event. A jet, in a sense, is a fossil of the hard scatter. It preserves the approximate direction and energy scale of the initiating quark or gluon, even though the initiating particle never exists as a free object. The jet's internal structure, how energy is distributed among its constituents, also encodes information about QCD radiation. Gluons tend to make broader, softer jets than quarks because gluons carry more color charge and radiate more strongly. Fragmentation is not an afterthought, it is the mechanism that preserves confinement. The more energy you inject, the more hadrons you manufacture. At higher energies, the parton can radiate additional gluons before hadronization, creating a branching cascade called a parton shower. That shower is calculable in parts, but it eventually enters a non-perturbative regime where models must be tuned to data. This is the first tension of the chapter. We can hit quarks harder than ever, yet the universe answers with composites, not with liberated constituents. The harder we strike, the more spectacular the final state becomes, but it remains stubbornly colorless. There is a quiet irony in the detector images. The most violent microscopic events still end as a crowd of ordinary hadrons. The fundamental objects announce themselves only through patterns. To loosen confinement in a different way, the LHC switches targets. It accelerates lead nuclei, each carrying many protons and neutrons, then collides them as flattened sheets. At ultra-relativistic speeds, the nuclei are Lorentz contracted, appearing like thin pancakes in the lab frame. When they pass through each other, hundreds or even thousands of particles can be produced in a single event. The visuals can show two heavy ions approaching, their internal nucleons smeared into a dense, overlapping blur. Unlike proton collisions, where a single hard scattering can dominate, heavy ion collisions create a bulk medium. Many partons interact nearly simultaneously, and the energy density can exceed the threshold where hadrons can no longer remain intact. The goal is not a single, clean scattering, but a controlled, measurable fireball. In lead-lead collisions, the goal is not a single, clean scattering. The goal is a hot, dense fireball, where quarks and gluons fill a shared medium. Temperature here is not a thermometer reading, but a way of describing the average kinetic energy and the degree of equilibration among many degrees of freedom. Lattice QCD calculations predict a crossover transition around a few trillion Kelvin, corresponding to energies of order hundreds of MeV per particle. That is the regime the LHC aims to reach in bulk. For a fleeting moment, the system crosses into the Quark-Gluon plasma regime. Deconfinement here is collective, meaning color is screened in bulk matter. The plasma is not a gas of free quarks drifting independently, but a dense medium where interactions are frequent. Screening means that the effective range of color forces is reduced because the medium rearranges itself to neutralize color over distance. In plain language, the medium hides color charges from each other beyond a certain length scale. This does not mean a free quark escapes into the detector. The plasma expands and cools, then hadronizes, and only colorless particles survive to be measured. The expansion is driven by pressure, and it happens extremely fast, like a microscopic explosion. As the system cools through the crossover region, quarks and gluons recombine into hadrons, and the familiar spectrum of pions, kaons, and protons reappears. The detector sees the end of the story, not the middle. So the experimental hunt becomes a hunt for signatures. The plasma is inferred from how it modifies jets, correlations, and particle yields. Each signature is a kind of shadow cast by a phase that cannot be directly photographed. The challenge is to separate genuine medium effects from ordinary QCD processes that also produce complex final states. That is why comparisons between proton-proton, proton-nucleus, and nucleus-nucleus collisions are so valuable. One signature is jet quenching, which turns a simple idea into a measurable imbalance. A hard parton produced early must traverse the medium, and it loses energy. The loss occurs through multiple mechanisms, including induced gluon radiation and collisional interactions with the medium's constituents. The parton is like a fast projectile moving through a dense fog, except the fog is made of strongly interacting color charges. In proton-proton collisions, back-to-back jets often emerge with comparable energies. In heavy ions, one jet can be dimmed, broadened, or partially absorbed. The event display can be shown side by side. In one panel, two clean jets balance like a scale, while in the other, one side looks ragged and depleted. The imbalance is quantified with observables that compare the transverse momentum of the jet pair, and the deviation from balance becomes evidence of energy loss. The missing energy is not destroyed, it is redistributed. It appears as many softer particles spread over wider angles, carried by the medium's response. That response can include a wake of disturbed plasma, a collective recoil that carries momentum away from the jet axis. In some analyses, the energy reappears as an enhancement of low momentum particles, correlated with the quenched jet direction. The medium, in effect, absorbs and re-emits the jet's energy in a different form. Jet quenching implies a dense, strongly interacting environment. A weakly coupled gas would not drain energy so efficiently from a fast quark or gluon. The strength of quenching suggests that the mean free path is short, meaning partons interact frequently as they traverse the plasma. This is one reason the QGP at the LHC surprised many expectations, because it behaves less like a dilute, weakly interacting plasma and more like a strongly coupled liquid. The data force theory to confront that strength. This result is one of QCD's strangest confirmations. The plasma behaves less like a transparent swarm and more like a thick, strongly coupled fluid. The phrase strongly coupled is technical, but the intuition is simple. Interactions are not rare corrections, they dominate the behavior. The medium is not merely a background, it is an active participant that reshapes the trajectories and fragment patterns of energetic partons. Even the internal structure of jets can change, with energy pushed outward and softened. Another signature is collective flow, which begins with geometry. Two nuclei rarely collide perfectly head-on, so the overlap region is almond-shaped. The initial energy density is therefore anisotropic, denser along one direction than another. If the produced matter were non-interacting, that shape would not matter much, because particles would stream out independently. But if the matter behaves like a fluid, pressure gradients translate geometry into motion. If the medium thermalizes and builds pressure, that shape becomes a push. More particles are emitted along the short axis because pressure gradients are larger there. The camera can show the almond-shaped overlap, then arrows indicating stronger outward push along the shorter dimension. Over time, the anisotropy in coordinate space becomes an anisotropy in momentum space, which is exactly what the detectors can measure. The medium turns shape into pattern. Experiments see this as correlations in the angles of many particles. The pattern is quantified by flow coefficients, and the strongest is elliptic flow. These coefficients, often labeled V2, V3, and beyond, describe harmonic modulations in the azimuthal distribution of emitted particles. Elliptic flow, V2, reflects the almond geometry, while higher harmonics can reflect fluctuations in the initial density profile. The remarkable feature is that these patterns persist across thousands of particles in a single event. Flow is not a single particle effect. It is a many-body statement. It says the medium acts collectively, converting initial shape into final momentum structure. In practice, physicists extract flow by studying two-particle and multi-particle correlations, carefully subtracting contributions from jets and resonance decays. The fact that flow appears even in small systems under certain conditions has sharpened debates about how quickly collectivity can emerge. Still, in heavy ions, the signal is robust and unmistakable. The magnitude of flow implies very low viscosity, close to a theoretical lower bound. In plain terms, the plasma is an almost perfect fluid. Low viscosity means the fluid does not resist shear strongly, so velocity gradients smooth out efficiently. In hydrodynamic models, viscosity controls how much the flow pattern is damped as the system expands. Matching the observed flow requires viscosities that are surprisingly small, suggesting rapid equilibration and strong interactions. Perfect fluid is a dangerous phrase if taken literally. It means the medium equilibrates quickly and transports momentum efficiently, not that it is calm. The plasma is turbulent in a quantum sense, filled with fluctuations and rapid microscopic interactions. Yet, averaged over many particles, it behaves predictably enough that hydrodynamics works. That is a profound statement. A system that exists for only a few femtoseconds can still develop fluid-like behavior. A third signature targets bound states that should not survive the heat. Heavy quark pairs can form quarkonia, like the J-Piz made of charm and anticharm. These states are special because heavy quarks are produced early in the collision, in hard processes, and then they experience the entire evolution of the medium. Quarkonia are therefore like thermometers that can melt at different temperatures depending on how tightly bound they are. Different quarkonium states have different sizes and binding energies, so they dissolve at different screening strengths. In ordinary conditions, quarkonia are held by the strong interaction, like a tight color bond. In a plasma, color screening weakens that bond over distance. The binding potential is modified because the medium rearranges its color charges around the heavy quarks. The result is analogous to reducing the range of attraction, making it harder for the pair to remain bound. When screening becomes strong enough, the state can no longer exist as a stable resonance. The analogy is electric screening in an electromagnetic plasma. Charges are surrounded by other charges, so long-range attraction is reduced and bound states can dissolve. In an ordinary plasma, this is described by the dBi length, a scale over which electric fields are screened. QCD has an analogous screening length, though the details are more complex because gluons themselves carry color. Still, the intuition carries. Beyond a certain distance, the medium cancels the force that would otherwise bind the pair. In QGP, the screening length can become shorter than the quarkonium size. The bound state melts, and its yield is suppressed compared to proton collisions. Experiments measure this suppression by comparing production rates in heavy ion collisions to scaled expectations from proton-proton data. The suppression is not uniform across momentum and centrality because the medium is not uniform and the production mechanisms are not simple. The pattern of suppression becomes a map of the medium's temperature history. Suppression is not a simple on-off switch because regeneration can occur. Charm quarks produced in the collision can recombine later as the medium cools. At LHC energies, charm production is abundant enough that recombination becomes significant, especially in central collisions. This means that some JP's mesons may be destroyed early and then reformed later, complicating the interpretation. Yet that complication is informative because it ties quarkonia yields to both deconfinement and hadronization dynamics. That complexity is part of the point. The data constrain both screening in the hot phase and hadronization pathways during cooling. Models must account for dissociation rates, transport of heavy quarks through the medium, and the probability of recombination at the end. The heavy quarks do not fully equilibrate like light quarks, so they carry memory of their passage. In that memory, the medium writes its properties. Across jets, flow, and quarkonia, the message is consistent. The medium is deconfined in bulk, strongly coupled, and short-lived. Each signature is derived differently, and each has its own systematic uncertainties. Yet they converge on the same picture. This convergence matters because no single observable is decisive on its own. Together, they form a coherent narrative of a phase that behaves unlike ordinary hadronic matter. Yet, the message also protects the central rule. Confinement is not defeated by clever engineering, because detectors still see only color-neutral hadrons. Even when quarks and gluons share a deconfined medium, the final observable particles are hadrons. The detector's raw output is a forest of tracks and energy deposits, and every stable or long-lived particle is colorless. The universe allows deconfinement as a phase, but it does not allow colored relics. The plasma is a phase of QCD, not an exception to QCD. When the fireball cools below the transition region, quarks and gluons reconfine into hadrons. The transition at vanishing baryon density is a crossover, not a sharp first-order boundary, meaning there is no single temperature where everything abruptly changes. Instead, properties evolve rapidly over a narrow range, and the degrees of freedom shift from quarks and gluons to hadrons. The language of melting is evocative, but the underlying process is a continuous reorganization of the medium. This is the second tension of the chapter. We can melt confinement with heat, but we cannot carry that melted state out into ordinary space. The plasma exists only while energy density remains high and the system remains small enough to stay hot. Expansion is relentless, and cooling is inevitable, so the window closes quickly. The LHC gives us a controlled glimpse, but it also reminds us how special the early universe was, when the entire cosmos shared similar conditions. The LHC therefore probes quarks without isolating them, and it probes deconfinement without exporting it. The universe allows a window, then closes it. That window is measured in femtoseconds, but it is long enough to imprint patterns on thousands of particles. The strange bargain of QCD is that it reveals itself through collective, emergent behavior. We do not see the quark. We see the consequences of quarks being unable to remain alone. These measurements do more than confirm a qualitative picture. They constrain the QCD equation of state, the relation between pressure and energy density. In hydrodynamic simulations, The equation of state determines how strongly the medium pushes outward as it expands. It also affects how quickly temperature falls and how long the system remains in the deconfined regime. By comparing simulated flow patterns and particle spectra to data, physicists can infer which equations of state are consistent with reality. That equation of state is a cosmological input because it shapes how the early universe expanded and cooled through the QCD crossover. Laboratory fireballs become calibration points for cosmic history. In the early universe, the expansion rate was set by gravity, but the pressure and energy density of the contents mattered for the details of cooling. If the equation of state changes rapidly, it can influence how fluctuations evolve, and it can affect the timing of when hadrons become the dominant degrees of freedom. The collider does not recreate the universe's scale, but it tests the same microphysics. The same data also test how quickly a QGP forms and how it returns to hadrons. Thermalization time, transport coefficients, and hadronization models are forced to match reality. Thermalization time asks how rapidly the medium becomes describable by temperature and fluid variables, rather than by free streaming particles. Transport coefficients, like shear viscosity and diffusion constants, quantify how momentum and conserved charges move through the plasma. Hadronization models describe the final conversion into hadrons, whether through fragmentation, recombination, or a mixture of mechanisms. There is a deeper implication hiding under the instrumentation. The most familiar matter in the universe is the low-temperature phase, where confinement dominates. The world of chemistry and biology is built from protons and neutrons, and those are themselves bound states of quarks and gluons. Confinement is therefore not an exotic phenomenon at the edge of physics. It is the everyday rule that makes stable nuclei possible, even though it remains invisible in daily experience. In that phase, most mass is not the sum of quark masses. It is field energy and motion trapped inside color-neutral states that cannot unravel. The up and down quarks in a proton have small bare masses, yet the proton is heavy on the scale of particle physics. The difference is energy stored in gluon fields and in the kinetic energy of quarks confined to a tiny region. Through E equals mc squared, that energy appears as mass, and it is mass that persists in every atom. Heavy ion collisions make that statement physical rather than philosophical. They show a medium where energy is carried collectively, then repackaged into hadrons as it cools. In the hottest phase, the relevant degrees of freedom are quarks and gluons moving in a shared bath. As the system crosses back into the hadronic regime, those degrees of freedom reorganize into bound states, and the mass spectrum of hadrons reappears. The collision is therefore a demonstration of how the same underlying fields can produce radically different emergent matter. So the question shifts from what we can see to what we can account for. If mass is largely confined energy, then what are you made of becomes a story about a rule. The rule is not written on the surface of objects, yet it governs what objects can exist. It decides that isolated quarks are forbidden in the final state, and it decides that stable matter must be color neutral. The LHC makes that rule audible because it forces the rule to act under extreme conditions. That rule is not only a prohibition against isolated quarks, it is a manufacturing constraint that turns hot, free degrees of freedom into durable matter. In the plasma, quarks and gluons are mobile and numerous, but they cannot remain that way as the system cools. Confinement forces them into hadrons, which then become the building blocks of nuclei. In a sense, confinement is the universe's way of packaging the strong interaction into stable units. This is why the chapter sits at the climax. The Collider is a human attempt to replay the universe's first microseconds, and the universe answers in signatures. The scale mismatch is enormous, yet the microphysics is the same, and that is the miracle of controlled experiments. We cannot enlarge the fireball to cosmic size, but we can enlarge our understanding by measuring its patterns. The detector becomes a translator between a vanished epoch and a present-day laboratory. Jets that should be sharp come out quenched. Correlations that should be random line up into flow. Bound states that should survive disappear, then partly return. Each of these outcomes is a constraint, not just a curiosity, because it limits what the medium can be. A transparent gas cannot quench jets so strongly, and a non-interacting spray cannot generate collective harmonics. A medium without screening cannot melt quarkonia, and a medium without recombination cannot regenerate them. Each effect is indirect, yet together they are hard to dismiss. They describe a deconfined, strongly coupled plasma that existed, briefly, inside our machines. The word briefly is important because the plasma's lifetime is short even by nuclear standards. Yet the system is large enough in particle number to behave statistically, which is why thermodynamic language becomes meaningful. The LHC creates a small universe, then watches it cool. And still, the final state is ordinary. The fireball cools, confinement reasserts itself, and the detector fills with hadrons, as if nothing exotic ever happened. The event record looks like a dense crowd of familiar particles, dominated by pions, with protons, kaons, and a zoo of short-lived resonances. Only by analyzing patterns, energy imbalance, angular harmonics, suppressed yields, does the exotic phase reveal itself. The extraordinary is hidden inside the ordinary. That ending is not anticlimax. It is the rule revealing its power. Even when we recreate primordial conditions, the universe insists on color neutrality at the finish. The detector, in effect, is a witness to the reassertion of confinement because it sees the moment after the plasma has vanished. The story is therefore not about escaping QCD, but about watching QCD change its face. How many other rules in nature are like this, inescapable, yet only visible when we push hard enough? Transition. We leave the collider and return to the human scale, where confinement is permanent and invisible. The visuals can rise from the detector cavern to the surface, then outward to ordinary materials, metal, stone, skin, each made of atoms whose nuclei are held together by the strong force. The roar of machinery fades, and what remains is the quiet persistence of bound states. The same confinement that ends every collision also holds every proton together in your body. In the next chapter, the accounting becomes personal. If most of your mass is confined field energy, then your substance is a consequence of quarks that cannot be alone. Hold a simple fact in mind, because it will quietly overturn your intuition about substance. Nearly all the weight you feel comes from protons and neutrons. Atoms are mostly empty space, with electrons defining size and chemistry as a diffuse quantum cloud. The nucleus sets mass, and the nucleus is made of confined quarks and gluons. Picture an atom in close-up, a tiny, dense core surrounded by a vast, mostly vacant volume. If the nucleus were a marble, the electron cloud would be a stadium, yet the marble carries almost all the mass. Start the accounting where intuition usually fails, and do it like a ledger. Up and down, quarks have tiny, bare masses, only a few MeV each. Those numbers come from the Higgs mechanism, but they are not what your bathroom scale is reading. They are closer to a seed value than a finished object. Add them inside a proton, and you still get only a small fraction of 938 MeV. The missing mass is not missing matter. It is energy made stable. E equals mc squared is not a slogan here. It is the bookkeeping rule that never blinks. Energy stored in motion and fields contributes to the rest mass you measure. In quantum field theory, rest mass is the energy of a system in its lowest overall momentum state. Even when the proton is at rest, its interior is not. Its constituents churn. A proton is not three beads glued together, and it is not a static diagram in a textbook margin. It is a dynamic bound state where quarks, antiquarks, and gluons continually trade momentum. The valence quarks set the proton's quantum numbers, like its electric charge and baryon number. Yet most of the proton's momentum is carried by gluons and the C, not just the valence quarks. That C is not poetic language. It is a measurable population of virtual quark, antiquark pairs. They appear and vanish within the limits allowed by quantum uncertainty, while gluons constantly split and recombine. The rest mass emerges from this restless balance, kinetic energy, field energy, and interaction energy locked into a persistent pattern. What looks like a single particle is a stabilized storm. Confinement is the reason the balance can persist as an object rather than dispersing. The QCD vacuum squeezes color fields into flux tubes that resist separation. Pull a quark, and the field does not thin out like electromagnetism, where lines spread and weaken with distance. In QCD, the field lines bunch, and the energy grows with separation. Keep pulling, and the energy in that stretched tube rises until it becomes cheaper to create new quark pairs. The vacuum itself pays the bill by converting field energy into matter. So the attempt to isolate a quark does not reveal a lone constituent waiting at the end of a string. It manufactures new hadrons, and the final state stays color neutral. This is why the rule feels like a prison and an engine at once. Confinement forbids isolation, yet it also guarantees production. The stronger you pull, the more matter you create. Now connect that microscopic rule to everyday substance, to skin and stone, and the quiet heft of a book. Your body's mass is mostly nucleons, and nucleons are mostly confined energy. Chemistry is electromagnetic, and it decides shape, bonding, and sensation at human scales. Weight is largely QCD because nuclei carry almost all atomic mass. Even the firmness of objects is mostly electromagnetic repulsion between electron clouds, not nuclei touching. Yet the inertia you feel when you lift something comes from the nucleus's energy budget. Even nuclear binding energy fits the same theme, though it is smaller by comparison to a proton's mass. The residual strong force is an echo of confinement, and small energy differences reshape nuclei. A few MeV per nucleon, gained or lost, can shift stability, radioactivity, and the pathways of stellar fusion. In stars, those tiny differences decide which elements can be built and which cannot. The universe, therefore, hides its fundamental ingredients inside composite objects, as if it prefers indirectness. What looks like solid matter is a stable pattern of fields. That idea has a history, because it took physics a long time to accept mass as something emergent. From early nuclear models to the rise of QCD in the 1970s, the story kept pointing toward energy as the real substance. Transition. We leave the collider signatures and return to the quiet matter they explain. The LHC never shows a free quark track, and it never should, no matter how high the energy climbs. It shows jets, narrow sprays of hadrons, scaling violations, and hadronization patterns that match quarks and gluons. On detector displays, those jets look like sudden blossoms of tracks, fanning outward from a point of violence. The underlying quark or gluon is inferred from the geometry, the energies, and the statistics. Deep in the data, Parton distribution functions reveal how momentum is shared inside the proton. They change with energy scale in a way QCD predicts because gluons breed at high resolution. Heavy ion collisions add a second line of evidence, and the visuals become almost geological. They create quark-gluon plasma, then watch flow, jet quenching, and quarkonium melting. The plasma behaves like a nearly perfect fluid, with collective motion that imprints itself on particle angles. Jets that should emerge back to back can be dimmed or distorted, as if the medium were a dense fog. These are indirect, but they are consistent across experiments and energies, and that consistency matters. They tell us quarks are real excitations, even when confinement hides them. So what is a quark in the world we actually inhabit, where we never hold one in isolation? A quark is a fundamental fermion field excitation carrying color charge and fractional electric charge. It comes in flavors, like up and down in ordinary matter, with heavier cousins that appear in high-energy processes. It also comes in 3 colors, not as pigments, but as the bookkeeping of the strong force. What is confinement, stated without metaphor, without prisons or strings? It is the observed property that isolated color does not appear, and only color-neutral states persist. QCD explains the pattern through a non-abelian gauge field whose self-interaction reshapes the vacuum. It predicts asymptotic freedom at short distance and strong coupling at hadronic scales. Asymptotic freedom means quarks act almost free when probed at very high momentum transfer, which is why scattering experiments can see partons. Strong coupling at larger distances is why the same quarks never escape. We can calculate many consequences, and lattice QCD reproduces hadron masses with impressive accuracy. Yet a full analytic proof of confinement from first principles remains open. That gap is not a failure of the theory's predictions, but a reminder of how hard nonlinear quantum fields can be. Even when the equations are known, the deep reasons can stay hidden. The map of QCD phases is also incomplete, like a coastline surveyed in patches. The crossover at low baryon density is supported, but the high-density region and any critical point remain uncertain. Now widen back to the beginning, when temperature was not a detail but a defining condition. In the first microseconds, the universe was hot enough for deconfinement in bulk matter. Quarks and gluons moved through a shared medium, not bound into individual protons and neutrons. The distinction between particle and plasma was blurred by sheer energy density. As expansion cooled the plasma, confinement returned and forced quarks and gluons into hadrons. That was a manufacturing step, not a detail. It turned diffuse energy into durable protons and neutrons, which later built nuclei and atoms. Without confinement, there is no long-lived matter inventory. Baryogenesis still sets the initial asymmetry, and we do not yet know how it happened. Confinement does not explain the excess, but it determines what the excess becomes. Ask the unsettling question that follows from that sequence. If confinement had been slightly different, would matter have remained a fog? Would chemistry ever have had stable building blocks to work with? Here is the payoff, stated plainly, with no need for mysticism. Most of you is not the bare mass of quarks. It is energy trapped by the strong interaction. Solidity is an illusion of fields arranged into stable, quantized patterns, repeated across trillions of nuclei. The stuff of you is a quantum prison that cannot help creating new walls. Answer the central question directly, because the mystery is sharper when the definitions are clean. A quarka is a fundamental colored field excitation, and it cannot be observed alone because the QCD vacuum enforces color neutrality. That prohibition shaped the cosmos by turning early energy into stable hadrons, enabling nuclei, atoms, stars, and chemistry. The universe does not just contain matter, it manufactures it through confinement. Transition. The smallest prison becomes the universe's most productive rule. Every proton in your body is a tiny echo of the early universe, carried forward into ordinary time. It is a cooled remnant of Quark-Gluon plasma, still humming with confined motion and fields. And when you feel weight, you are feeling that hum made steady. Energy organized so reliably that it passes for substance. The question is not why matter exists, but why the vacuum allows it to stay. We followed the trail from atoms we once argued about, to nuclei we could finally probe, to protons that stopped looking like beads and started looking like storms. The deeper we pushed, the clearer the pattern became. Not a ladder of smaller marbles, but a set of fields whose excitations only make sense in company. In QCD, quarks and gluons can behave almost free when you strike them hard enough. Yet the moment you try to separate color for good, the vacuum answers by tightening into a flux tube, then paying the energy back as new quark-antiquark pairs. That is why the evidence arrives indirectly, in scaling curves, in symmetry multiplets that predict new hadrons, in jets that remember a parton's direction, and in lattice calculations that reproduce masses without ever releasing a single quark. It is also why the strong force has two faces, a fundamental color force carried by self-interacting gluons, and a short-range residual echo that binds protons and neutrons before saturating. In the first microseconds, the universe briefly escaped this rule in bulk, forming a quark-gluon plasma, where color is screened and matter flows like a near-perfect fluid. Then cooling carried everything through the QCD crossover, and confinement returned, reorganizing that soup into hadrons and minting most visible mass from trapped energy rather than bare quark masses. Even now, our story ends with open doors, an unproven theorem of confinement, an incomplete phase diagram at high density, and baryogenesis still whispering about why any of this matter survived at all. So what is a quark, and why can it never be observed alone, if it is as real as anything in physics can be? A quark is a fundamental excitation of a quantum field with color charge, and the universe forbids its isolation because separating color does not weaken the strong force, it concentrates it, until the attempt to look becomes the act of making new, color-neutral matter. In the end, the cosmos did not merely inherit matter, it manufactured it through a constraint, turning separation into creation and energy into mass. You are made of prisoners, yes, but more deeply, you are made of the law that keeps them together. And in that confinement, the universe found a way to become solid. If you want to keep pulling on this thread, follow the next clues. From heavy ion collisions and future density scans to the unanswered riddle of baryogenesis, and ask what other rules might still be building reality in the dark.